countdown says 1 minute. It's wrong. The countdown is now at 6 minutes. Does anyone know any good jokes? We have 3 lovely medals here for the winners, as well as this wonderful trophy. If you haven't seen the trophy yet, you might as well come see it now. We've got 5 minutes to kill. The list of all Google CodeJam winners since 2003. Your name could be the next one. You could have this lovely gold medal. Finch champion. Everybody go.
It's final button for that. But yeah, it's only for people with very small necks. So did you read the terms? We have 100 pages of terms.
Go upstairs and take anything.
Good roll.
You want to play them? Yeah.
I'd rather reread. Well, good question. I try to read them once in a while. What's up?
How many of you are using Checkerboard or Allergy idea? Raise your hands. Igor, Checkerboard and Allergy idea. Are you using it?
Is that bad?
No, just if someone uses it, then he makes sure that it doesn't send statistics to itself. No.
This guy who's smart idea. Yeah, that's great. Very, really helpful library for all the other people. You solved everything.
Yes.
I'd like to think that he turned it off for the.
But it's still open source and
Okay. All right. So as long as the version you make available for download is the same version people are actually using. That's good, yeah. Yeah, it's not a problem because after we gave the problems to Petya and he couldn't solve them. So that's the teacher.
Can everyone please double check to make sure that your monitors are recording? Make sure that you're recording what's on your screen. We don't want to miss out on the exciting coding action. You know, there's going to be like a 4-hour video on YouTube of each of you. So if someone wants to watch that, that is like, wow, 4 days of back-to-back viewing of people solving programming problems.
Good afternoon, and welcome to the finals of the 2014 Google Code Jam. I'm Christian Howard, and sitting next to me is John Dethridge. And together we're going to be your hosts over the next 4 hours as we stream live from the Google Los Angeles office located in Venice, California. I think we have a lot of exciting things planned for the next 4 hours, including overviews of the problems that the contestants will be having. We're going to have a few Code Jam engineers come in. We can talk to them. And we're going to have some interviews of Googlers from the LA office to learn about the projects they're working on here.
That's right, and also we'll be checking on the scoreboard, of course, and talking about how the competition's going, what all the coders are doing, what the problems are that they're solving, and just generally how a programming competition works for those of you who aren't familiar with them. We'll also be answering some of your questions if you want to send them to us with hashtag CodeJamFinalsQuestion. So this is the 11th year of the Google Code Jam. 50,000 people registered almost in the first round, and now we've whittled it down to these final 26 who are competing for the bragging rights of being the Google Code Jam champion.
Now, Code Jam isn't just about being able to code well, right? I mean, you have to have precision, speed, a general mastery of mathematical concepts to really kind of solve these, they're fairly intense puzzles, right?
Right.
Now, there's also a lot of strategy in Code Jam, and I'll be picking your brain about that because I'm not as familiar with it. But for example, when you submit a solution to a problem and related to other people in the room. Now, in addition to the bragging rights of being Google Code Jam champion, the winner takes away $15,000, second place takes away $2,000, and third place takes away $1,000. Now, of course, all of the contestants have been flown to LA to compete here. And they'll be going on a tour of Universal Studios, and perhaps the best prize is a limited edition Code Jam t-shirt. Now, I just want to point out that although it's really an intense competition and people are working very hard, all the people who participate in Code Jam are part of a growing community of friends, engineers, problem solvers from around the world. Now, John, you have been involved in Code Jam in one way or the other since its inception. Can you give us a little history about Code Jam, how it started, and how much work goes into it?
That's right. So originally, the Google Code Jam was outsourced to Topcoder. They ran the competition, but Google has a lot of programming competition enthusiasts working here. So we decided that in our 20% time, we were going to put together our own competition. So 20% time is Google's program where people can choose a project they're interested in that's outside their usual job and spend 20% of their time building that. So there's been various volunteers across Google putting together the competition application on Google App Engine and writing the problems and solving the problems and basically putting on the whole show.
So you mentioned 20% time, so it's fair to say this is a labor of love. Everyone who works on this, they're doing it because they're very passionate about the community and just the type of skill it takes to solve these kinds of puzzles. Can you tell me, it's now August and we're in the finals, how long does it take to actually go from start to finish in designing these puzzles for the contestants?
So we actually get started basically at the beginning of the year in January. Anyone across Google can submit problem ideas, and then other people start solving those problems, and then a group of us get together and decide on sets of problems that we're going to put in each round. So we started several weeks ago with the qualification round, and we put in a relatively easy set of problems for that. And as the field gets narrowed down, we set harder and harder problems until we get to the finals, where we've set 6 really quite difficult problems.
No, so is it dynamic? So, for example, if you have one particular round that people solve very easily, do you really kind of crank up the difficulty for the next round?
We do keep an eye on how well our expectations are matched. So we looked at the previous round at how many problems the top 26 solved to sort of get an idea of whether we think they're going to solve all of these problems that we've set on the final. But you never know, maybe no one will finish the problems today, or maybe we'll get several people finishing them all. But that would be pretty impressive.
Interesting. Okay, so the competition just started within the last 5 minutes. But prior to that, there was some setup. So what goes on there? So the contestants are brought in and...
Yeah, so the contestants each have their own computer, and they can tell us ahead of time what operating system they'd like installed, what text editors they'd like to use, what language they want to code in so that they have the compilers that they want. And then they get some time just to configure everything, make sure it's all working. We start sort of a test contest so they can make sure they can get to the website and all the procedures are working for them and everything. So when the competition starts, as you can see back there, they're all ready to go, and they've got an environment that's that's similar to what they'd use at home. So they've got all the tools that they think are best for solving these problems.
So you've competed before, so as you just saw in the room right there, that what's going on in their minds strategy-wise?
Yeah, so at the moment you can see most of them are sitting there reading on their monitors. They're looking at the problems. We've set 6 problems in this round. So they're sort of reading each one, getting an idea of what it takes to solve the problem, and maybe making some notes about how they might go about solving it.
And that's the previous year's champion right there. We'll get to that in a second.
That's right. There's even Miatselski. So he's reading. I can't quite catch which problem it is. I think it's the first one, and he's making some notes, thinking about how to solve it. So usually these problems, it's fairly clear what the problem is asking them to do. So they know what the program they'll write has to do, but it's not so clear what an algorithm could be that could solve that problem. So they often drawing diagrams, writing equations, figuring out what they're going to have to do. And so this is early on in the contest, so they're probably going to take a look at a few problems, probably at least the first 2 or 3, get an idea of what it is they have to do, and then pick one to start working on.
And they have to actually pick, so there's 2, if you can explain, there's 2 data sets for each problem.
That's right. So the scoring system's a little interesting. So for each problem, we've assigned a different number of points, and also there's 2 inputs that they get to solve. So it's almost 2 sub-problems. That's called the small input and the large input. And so the small input, as it sounds, that the cases are smaller. So the problem is to just come up with a program that gets the correct answer at all, and it doesn't have to be as efficient as possible. Right. It mostly just has to be correct, and so that's not worth as many points, but they have to do that first, and then if they get the correct answer to that one, they can move on to the large input, where it's much more difficult. They have to possibly rewrite their program to be faster, or if they've written it from the beginning to be fast, then they'll be okay. The other feature about the 2 different problem sets is that for the small input, they get to try, and then we'll tell them whether they got the right answer. So if they get it wrong, they can try again. They can try and figure out what the bug is, what's wrong with their program. And then when they finally get the right answer, they get those points, and they know they've got it. But the large input, we're a lot more harsh. They only get to try it once. And we don't tell them whether they got it right. They send us their answer. We put it on the scoreboard that says they solved this large problem. It would get them. Or they
submitted a solution.
Yeah,
yes.
They've submitted their problem. They get the points show up on the scoreboard, but they haven't really got them yet until after the contest, where we go through them all and announce which of these solutions were correct. So they really have to be sure that they've got it right, because they only get that one chance. And if their program runs too long and it hasn't got the answer, or if there's a bug that they hadn't realized yet, then they're not going to get those points. They're going to get 0 for that. So there's a bit of strategy involved in how long you'd spend testing your own program. A lot of people will write their own test cases and throw them at their solution, try and make sure that they seem to be getting the right answers. But the clock is ticking, and there's only a limited amount of time for them to solve more problems. They don't want to end up solving fewer problems because they spent so long testing. And also, if the multiple people have the same number of points at the end of the competition, then we tie break by who got to that first.
Right.
So there might be 2 people racing to finish the last problem, and if they let the other person submit first, then they're going to win, assuming they've got all the questions right. And
so also there's the added restriction that for the large input, their code has to finish within 8 minutes, correct?
That's right, yeah. They have 8 minutes. That's from when they say they've finished the problem, they go to the website, say, I've finished this, and then it sends them an input file. And they run that on their program, because they're allowed to use whatever language they like. So They compile their program locally. They can use whatever options they like. They're free to choose that. So they run their program. They need to send us the answer and their program within the 8-minute time limit. And for the small input, it's only 4 minutes, but it's usually fairly easy to get it to finish within 4 minutes. But they get to try again, of course, so it's not as stressful.
Okay, so that's where, you have to be efficient too. I mean, I find this incredibly fascinating. But we showed earlier, we saw the previous year's champion, Mystic is his handle. We're going to introduce a few of the other contestants. Like John said, there's 26 total. We're going to introduce 6 of them next. One thing I do want to ask is they all have names, of course, but they all have handles. Is there anything significant to a handle?
Yeah, so the competition takes place over the internet, the early rounds. So people often use a nickname, use a handle on the internet. So some people have signed up with just their actual name. Other people have used their.
And that was your handle. Your personal handle was your name.
Yeah, I just had my name. Wasn't very interesting.
Well, Deathridge is a cool name, so.
Well, thanks. Yeah, but a few of them have interesting nicknames. I'm sure there's stories behind some of them. I'm not sure we know.
Well,
what they are,
let's
really.
see if there are any. So we do have the first 6 contestants we're going to show you. We start with Mystic. And Mystic, Ivan Miatselski, is from Belarus. He's a researcher for a hedge fund company in New York. And as I said, he's a piano player, but also last year's champion. Of course, he qualified this year.
That's right. So we actually have a new rule where the previous year's champion gets an automatic berth back to the finals. But interestingly, he made the top 25 anyway, so he didn't even need that rule. But that was lucky for whoever came 26th, because we just decided to invite whoever came 26th to round out the numbers.
Next up, we have Kenny Horror as his handle. And I'll let you take this name.
Andrei Malovich.
I think that's right. Also from Belarus, and he's a software engineer at Facebook.
That's right, a lot of interests there. Playing guitar, ping pong, cycling and snowboarding. I'm sure he'd like to be outside. The weather's pretty nice here in Los Angeles, just a couple of blocks away. There's Venice Beach. There's people playing beach volleyball and swimming and surfing, but
Not these people.
no, they don't get to do it. Well, if they finish early.
If they finish early, they can maybe do
Bit of
that.
an extra incentive to get everything done while the sun's still shining. They can go out and take a break, yeah.
All right, next up we have, I don't know if this is the right way, but KCM 1700, Chan Min Kim from the Republic of Korea. And he's a student at the Seoul National University. His interests are solving Rubik's Cubes, and there's a lot of algorithmical principles behind Rubik's Cubes, which I find interesting. And playing rhythm games like Jute Beat and Reflect Beat. I'm not familiar with either of those.
Yeah, I haven't played them either, but yeah, a lot of these guys like computer games. They have some of those sort of interests. Yeah, and a lot of them are students, as we said. Yeah, so there are competitions, separate competitions at the high school level and the college level. A lot of these people have been training pretty hard for those, and so they're easily the equal of us professionals, and yeah, often beat us. So yeah, I think we're even about half students here.
Interesting.
26 finalists.
Our next participant is Dmitry Egorov. Did I pronounce that correctly?
Yegorov, I think.
Egorov, okay. He is another student from Russia. And fun fact, he was the 2014 ACM ICPC World Finals champion. And ICPC, that's another coding challenge.
Yeah, that's one of those college level competitions I was talking about. So yeah, that's a great achievement. That wasn't too many months ago, I think. So he's certainly well practiced at the moment. I think if that's him there, he's already typing. So he, although he's pressing the arrow keys a lot.
Yeah, I was
Maybe
going to
actually
ask.
just scrolling around the problem. I'm not sure, but anyway, he looks pretty animated there. It looks like he's got started pretty early on. We're only a few minutes in.
Next up, we have Julkakov, is the handle.
Dmitro Julgakov.
Yeah, I hope that was correct. I'm from Ukraine, and he's another software engineer at Facebook. And his fun fact is his favorite coding language is C++, which is, would you say C++ is the most commonly used language in this?
I think it is, yeah. We asked each of them what language they thought they'd use. C++ is pretty common, partly for execution speed, partly, well, it's just what people are familiar with. We do write the problems so that they're solvable with a wide range of languages. If people want to use Python or Java, it won't be a problem, but yeah, people choose what they're most comfortable with.
Well, and the majority of these contestants, they know a vast array of languages. I think you were showing me last night that there's some people who have one contest like with 17 languages that they code.
Yeah, actually a lot of people, because we do say you can use any language you like, some people have fun with that, especially in the early rounds where the problems are a bit easier, and we'll try solving every problem with a different language, sometimes very esoteric ones with profane names that we can't say. But yeah.
Well, you showed me the language I'd never heard of last night, Shakespeare, where you're actually writing
right, yeah,
as it's...
The
and
program looks like a Shakespearean play.
Yeah, which I thought was hilarious.
It's crazy.
And next up we have Sidya. I'll let you take the pronunciation there.
Dmitro Sobolev from Ukraine. Yeah, another C++ coder.
Yeah.
A fun fact is he's got an identical twin brother.
Oh, we should see if his twin brother is into coding.
That's what he
too.
looks like there, you can see.
Yeah.
And, he's hard at work as well. And yeah, so we had a couple of Facebook engineers there. Facebook actually run their own programming competition as well.
Mm-hmm.
I think most of the winners have so far been Google engineers. So
At the Facebook, yeah.
I would be surprised if Facebook are going to try and pay that back by winning our programming competition. Obviously, Google employees can't enter our own programming competition, but you know, as a consolation, you can help run it and write the problems. Yeah.
And we just want to remind anybody who's watching on the live stream that we will attempt to answer any questions that come in. If you have any questions on how CodeJam is run, or what people are doing, you can submit your question to, it is hashtag
CodeJam finals question.
Yes, finals plural, question singular. And any questions, we will try to field, and we'll be doing that all day.
That's right. Yeah, let's go back to the competition room, maybe have a look at how the whole room's set up. We've got sort of 26 computers there.
And yeah, they're really intense, and I can imagine you can't really hear anything in there as far as, it's just silent.
Oh yeah, pretty silent, everyone concentrating pretty hard.
It's right off the bat. When we come back, we're going to have an animation of one of the problems that we'll be solving, checkerboard matrix.
Yeah, we're going to explain the problems a bit while you're watching, so you get an idea of what it is these people are doing.
So join us in about 10 minutes, let's say 1 o'clock, and we will go over checkerboard matrix.
Yep, we'll see you all then.
Welcome back. So it looks like we already have some submissions on the
We have
scoreboard.
some action on the scoreboard already. So quite a few people, 13 people have solved the first question called Checkerboard Matrix already. It is the easiest problem, and yeah, you can see the times there. Yegor Kulikov got the problem, the small input in 6 minutes and 45 seconds.
That's very
Pretty
fast.
impressive, and then the large input just a minute later.
Now, as you said before, we don't know if the large input is correct or not yet.
That's right, so you can probably see the question mark
Yep.
there instead of a tick. So we won't know whether they've got it right until the end. And it's possible some of these people have submitted a bit too quickly without really checking and aren't going to get those 9 points. But probably they're okay for this problem because it's not all that difficult. And if you solve the small input correctly, you're probably going to get the large input. Although you'll notice towards the bottom of the scoreboard, there's 3 people who got it wrong on the first try. So they obviously missed something, had an algorithm that wasn't quite correct in every case, and so they had to correct it and submit again.
So only 13 have submitted out of the 20. This first
That's
problem,
right,
as
out
it
of
looks
the
like. Am I reading that
26.
correctly? Okay. Well, okay, that was a lot quicker than I thought. But we were going, this problem that they have solved, Checkerboard Matrix, we're going to try to explain that a little bit better and bring up, there we go. All right. So, as we said, one of the problems here is called Checkerboard Matrix. And the goal of this is to find the fewest number of moves to transform a defective checkerboard into one with alternating squares. As you can see, on one side you have a checkerboard with the white and black squares all mixed up, and the goal is to switch over to what the traditional checkerboard would be. Now, this being a programming competition, the white and black squares are represented by 1s and 0s. This is a binary matrix. And so the contestants must fix it so that the entries alternate between 0 and 1 along each row and along each column in the fewest number of moves. Now, you define a move as swapping any 2 rows of the matrix or any 2 columns of the matrix. For example, in this simple 4x4 binary matrix, it takes 2 moves, a single column swap and a single row swap. And the end result is a nicely alternating binary matrix. Now, contestants are given an input file. So they're given T as a number of test cases to solve. And for this problem, the limits are T can be from 1 to 100. So for each input, they could have 5 or they could have 100 test cases to solve. And each test case consists of an integer n. So for the small data set, n can vary between 1 and 10. And for a large data set, n can vary between 1 and 1,000. Okay? Each one of those integers is followed by 2n lines, so it's an even matrix. And so you can see the output for these 3 examples. In the first one, it's already alternating that 2x2 matrix of 0, 1, 1, 0. You don't need any moves to make that complete. The second test case is the one we just showed you. It took 2 moves to make that. And of course, in the third matrix, it's all 0, so it would be impossible to actually solve that. So it seems like a very simple problem, and as is the case with all programming challenges, for small cases, it is simple. But things can rapidly get much, much larger, and that's when you have to be very efficient, very precise, and really know what you're doing.
That's right. So that's the next problem.
That's
We'll
our next
probably
problem that we're going to be
explain that
talking
one
about.
a bit later. So just now, Dmitro Sobolev has actually submitted another problem, problem D. There's small input at least, so that problem's called paradox sort. We'll be talking about that later. So I think what he's realized is that the small input here is actually very small. I think it's something like a vector of only 12 numbers, and you can solve the problem by trying every permutation of those just about and seeing which one gives the right answer. So he sort of quickly picked up those points and got it out of the way. Also, Yegor Kulikov has solved the small input for problem B, putting him in second place.
And which is problem B?
Problem B is power swapper. We haven't talked about that one.
We haven't talked about that one. We'll get to that one a little bit later.
Yep.
We want to keep you hooked, and we're going to keep you here for 4 hours, so you have to wait for that one. I think it'd be a good time to see if we have any questions from the audience, actually. So we do. We have a question here, and I think it's a very good question, actually. It's encouraging people. So someone says, Abdul Basif, I hope I pronounced your name right, Abdul. I am not a programmer, and I want to join next year's Code Jam. Which language should I select?
Well, yeah,
I guess to rephrase that, what would be, if you have little to no experience in programming, what would be a good accessible language to start?
That's a good question. So a lot of people might say Python. I started with BASIC when I was little. I don't know if anyone still uses that, or Pascal. You could start with C. I think there's a lot of courses online that just choose a language and work through some exercises and teach you what to do. But yeah, you can have a look at a few languages and decide what you like the most.
And of course, we encourage anybody of any skill level to at least try the qualification rounds, right?
Yeah, so the qualification round runs for, I think, a whole day. So you have a lot less time pressure, and you can just try these problems and keep retrying those small inputs until you think you've got, until you get the right answer. So yeah, there's certainly time to start practicing now and be good enough to do okay in the qualification round next year.
Yeah, and it's good experience. And sometimes you don't learn something unless you actually are given a problem to solve. So yeah, Abdullah, I'd pick a good language, pick Python maybe, and just start poking around. There's a lot of good online tutorials. Thank you for the question. Let's see if we can go back to the competition room and see if anything's kind of heating up or if it's still very, very intense. That looks like an intense pose. Do you know who that competitor is by recognition? I can't make it out, no.
I think he's working on a solution.
All right, so we're going to leave it to the competition room. We're going to take a break. When we come back at 1:20, we will go over another problem. This one is called symmetric trees. So stay tuned. Welcome back. Just joining us randomly is Bartholomew Furrow, who is one of the top CodeJam engineers, and he's come by, and it's fortuitous because he's going to help explain one of the next problems, allergy testing. And I believe this is something that someone close to you came up with, but...
Yeah, so actually I came up with this problem it's based on a true story having to do with my wife, Kelly, and an allergy or sensitivity that she thought she might have. And it turns out there are whole lots of different kinds of food, and we wanted to figure out what she would react to. So in this problem, the main character, also named Kelly, has a certain number of different kinds of food, N, and N could be very large. There could be 1 million different kinds of food or even more. And she has to figure out which one she's allergic to.
So we have some slides for that.
We have some slides for that.
We're going to show a diagram.
Well, we'll continue to go on. There we go.
There we go. So the way that she figures out whether she's allergic to a particular food is that she'll eat some number of the foods. She might eat 1, she might eat 2, she might eat 500,000 of them. And if it turns out that she is allergic to one of the foods that she ate, it's going to take her A days. So A is just some number of days, could be 5 days, could be 100 days, until she can try again and try to figure out which one of those foods was the problem. Or if she doesn't have an allergic reaction, then she waits. I'm sorry, I have that backwards. I got A and B backwards, but there's a different number, which is how long she has to wait if she does not have an allergic reaction.
Right.
And so
Just
the
to
idea,
see if the food, she has to wait a certain amount of days to see if she does have a reaction before moving on to the next test.
That's right. And if she doesn't, and if she does, then she has to wait a certain number of extra days to get over the reaction before she can start again. So then the question is, how long does it take her if she makes the best possible choices to minimize the time? How long does it take her to figure out what she's allergic to?
Interesting. So for example, like in the simplest example of, 3 food items, right? You can try, one strategy would involve trying 1 at a time, or one strategy would be like, let's take a group of 2.
That's right. So one strategy, so let's say her strategy is that she'll eat just the first food item. If she's allergic to it, then she'll know that after A days, and then she's done. Okay. And she's successfully got the answer. If she's not allergic to it, she still has to wait 8 days to be sure that she's not allergic to it, and then she still has to figure out the difference, figure out which of the other 2 food items it is. So in this case, she tries the apple. After 8 days, she realizes she's not allergic. Now she still needs to know if it's the artichoke or the eggplant, and she has to eat one of those.
Right. So I can see with 3, this seems almost trivial, but when you start getting to what the contestants are seeing as an input, it becomes much more difficult.
It's a lot more difficult. So we can see the example cases on the screen right now. And in this example, it's sort of laid out in a maybe not an obvious way. But if you look at the second and third lines, on the second line of that's labeled input, it says that there are 3 different foods. And when Kelly eats one and is not allergic to it, it takes her 1 day to figure that out. And if she eats one and is allergic to it, it takes her 10 days to clear out her system. So the numbers that the contestants might be seeing get really high. For the large data set, there could be up to 10 to the 15 foods, which is, I think, 10 quadrillion, which is a bigger number than most of us ever have to deal with. And as for the number of days that it takes her to figure out whether she's allergic or not, that can go up to 1 billion. So we're really, I mean, the examples get a little less realistic, but you can tell that we're dealing with really big numbers here. And so a sort of naive algorithm of let's try everything, let's try all the different possibilities isn't going to work because there's simply too many of them.
Yeah, if you have 10 of the 15 foods, you're not going to be able to eat 1 a day.
It's going to take a while. Well, the answer could potentially be very large. And maybe the answer will be it will take her 1 trillion days to figure out which food she's allergic to. And that's okay. But you don't want to say, well, there are 1 quadrillion different foods. Should she try eating just 1? How long would that take? Should she try eating just 2? How long would that take? And ask the same question again 1 quadrillion different times. Computers are fast. They're really fast. They can do 1 billion computations a second, give or take. But this would take a computer like that 1 million seconds to try out all those possibilities. So that's way too slow. So this is an example of a problem where you can come up with a solution that would solve this problem for a smaller case, for a smaller data set, but we've really pushed the limits and we've asked for the answer to a very big number.
That's right. Yeah, this problem started off its life as a much easier problem because those limits were much smaller and we were thinking maybe we'd put it on an earlier round. So that an algorithm that took order n squared time, to use the maths, would be fast enough. But then we thought of faster techniques to be able to solve this problem, so we made it a bigger challenge by raising those limits.
So modest, John. You were the one who thought of the faster techniques for solving the problem. So yeah, in the first case we had n at something like 1,000, and we thought a dynamic programming approach, which is something that all of our contestants would be very familiar with, would solve the problem. Where you, in the dynamic programming approach, you would figure out the answer for if you had one food, how many days would that take? 2 foods, how many days would that take? And you'd base that answer on the answer for 1. And you just keep going. And by the time you've gotten to 1,000 foods, you're trying out a lot of possibilities, and you're basing the answer on the answers for 999, 998, etc.
Yeah.
So that's how you do the dynamic programming solution. And this sort of try everything would work if there were only 1,000 different kinds of food. John realized something crucial about how you could speed that up a lot, and we were able to raise n to up to 10 to the 15. And then a little more recently than that, we realized we could take our A and B values up to 10 to the 9, which really cranked up the difficulty even further. I'll be really interested to see whether any of the contestants can solve this problem.
Yeah, so now it's less of a standard problem, and something where the competitors are really going to have to get some insight into the mathematics of this, into the structure of this function, from the number of foods to the number of days that it's going to take to solve it.
That's exactly right. I mean, this isn't something you can simply look up in a textbook. I think that if you were to show this problem to the best computer scientists in the world, which we kind of have. We're showing it to our contestants, and we've shown it to the Googlers who prepared it, who are some really excellent competitive programmers. No one had solved this problem probably before we asked them this contest.
This is an original challenge for them, and I think that's what a lot of these people find the most interesting who've entered. They want to see something where they have to use some creativity, come up with a new technique that they hadn't thought of before in order to solve the problem.
And maybe it's a technique no one's ever thought of before or ever used before.
That's possible, yeah. So far, actually, the small input has been solved by Gennady Korakevich.
If we can take a look at the scoreboard, yeah, we have some scoreboard updates.
Yeah, he's also solved the small for allergy testing and for paradox sort. We haven't explained that problem yet. So not sure what he's working on now. He might be working on the hard input for one of those. Oh, actually, he's gone to problem B, to power swapper. So it looks like Gennady's taking a strategy of solving a lot of the small inputs first. Probably when he read the problem, he could see think of an algorithm for the small inputs fairly quickly. So he's sort of getting them out of the way, getting those points on the board. And I guess then he'll take a look at how much time's left and decide which large inputs to work on.
We have a question actually from our audience, and it's related to the scoreboard. It says, Igor has time expired in the second problem. Does that mean he cannot submit a solution anymore?
Yeah, I'm afraid it does. So what's happened, he solved the small input correctly, and then I guess he's thought that his solution was correct and fast enough to solve the large input, and he's downloaded it, and something's gone wrong. He hasn't been able to.
So he exceeded that 8-minute limit?
Yeah, the 8 minutes must have expired. So either his program was slower than he thought it might be in the worst case, or he found a bug and just wasn't able to fix it within the final 8 minutes. So hopefully this doesn't set him back too far. It is only the second problem. There's 12 points for the large, and there's a lot of other input cases that are worth way more than 12 points.
Yeah.
So if he manages to solve more problems than everyone else, he's still in the running.
Now, there's another question from Ankit Sablak. I hope I pronounced that correctly. They ask, I think Google places a lot of emphasis on dynamic programming problems. What topics do you recommend someone study in order to get a good hang of problems that surface in these programming competitions? Yeah,
so I guess dynamic programming comes up as a technique a lot. Well, we were just saying that problem allergy testing originally was a dynamic programming problem, but we actually made it a lot harder so that doesn't work. I think the important thing with studying a lot of the fundamentals like dynamic programming and a lot of graph algorithms and mathematical algorithms are understanding them really well, so you can tailor those to create new algorithms to solve these different problems. I mean, the early rounds, the ones where we had 50,000 people or thousands of people, some of those problems will be solvable by fairly standard techniques. But once you get to this level, to the final of this competition, or in the other big competitions, you really have to be coming up with something new that you haven't seen before. So a strong familiarity with these algorithms and how they work. is sort of what will give you a good foundation for thinking of modifications of other things or completely new algorithms that will solve these problems.
This was another question, sorry, but it's something that I'm very interested in. I think I've asked before, but how much different are the problems that are solved at Google compared to the problems that are given in CodeJam?
That's a really good question. I think when you are able to solve CodeJam problems, that really gives you a toolbox full of things that you can apply at work. And just problems that otherwise might be challenging or might require a lot of thought at work, because you've seen boiled down or even more complex version of those problems on programming competitions like CodeJam, then that's really helpful. I think that there's certainly much more to what we do at work than programming competitions. I've worked on machine learning projects. I've worked on just a variety of collections of signals and synthesis to produce things to help us decide which ads to show is my main project. And that stuff isn't stuff you'd ask in a programming contest, but I really feel like I built a strong foundation from competing. Personally, I was a physics student with a passing interest in programming until I discovered competitions. My problem was I took a computer science course, and I thought this was a really neat thing, this computer programming stuff, but I didn't have anything I wanted to do with it. I had no problems that I wanted to solve. I had no apps that I wanted to make. And then one day I stumbled across a poster advertising a programming competition. I thought, oh, why not? Let's give it a try. And it was a lot of fun. And then all of a sudden I had thousands of problems I wanted to solve with computer programming. And so it really got me engaged in it. And I ended up competing in the first CodeJam back in 2003. And got maybe a little bit lucky and got into the finals. And that's how I ended up as a computer scientist at Google. So it really did build the skills that I needed, even though there are, of course, more skills on top of that, but I felt like it really gave me a strong foundation.
Would you say the same thing?
Yeah, I think sometimes these sort of algorithmic things do come up. So on Google Maps, you're trying to find a sort of an efficient route from one place to the other. Sometimes range trees will come up as a good way to analyze the structure of web pages, or we might have some min cost max flow algorithm that tries to compute better answers. And we care a lot about efficient algorithms at Google. We're trying to return answers to people's queries within milliseconds. So if we can think of techniques to get better answers that run fast enough, then that's a big help.
Yeah, interestingly, and I remember when I first started at Google, I had this idea that I really wanted to work on user-facing stuff, like projects that mom and dad could use. And there are a lot of really exciting projects like that. But one of the really interesting things is that infrastructural behind-the-scenes projects very often have these really interesting algorithmic challenges. And I mean, your customers aren't mom and dad, but the other software engineers at Google. But you can really get into some meaty algorithmic problems like that. And a lot of great competitive programmers at Google work on that sort of thing.
Oh, cool. Thank you so much for stopping by, Bartholomew. Stay tuned, because next we're going to have an interview with the Signals team with Brian Milch, and that will be at 1:45, so roughly 10, 15 minutes away. Until then, if we can get a shot of the room, you can see what the coders are doing. Welcome back. As promised, we have Brian Milch sitting with us. He's from the Signals team. And first off, I'm just going to ask, what do you do on the Signals team? What is the Signals team?
Yeah, so there are a lot of groups at Google that need to be able to tell what a piece of text is about, whether it's a web page or a search query on google.com. You know, what are the topics of this piece of text? And so we provide signals that help other teams to make those determinations. An example of this is if you're an advertiser and you want to show ads on the Google Display Network, you know, other web pages that get ads from Google. One way you can do that is by topic. So you can choose from this hierarchy of categories, everything from basketball to investing to gardening. And then, you know, we on the back end have to be able to say, okay, here's a page, we need to show ads on it. Is it basketball or is it gardening or what is it? And so that's one example. Another example is if you're searching and you enter a query about golf, say. Well, there's going to be lots of different pages that mention golf, maybe. They mention that somebody likes golf or some business deal was made in a golf game. But what you really want is pages whose main topic is golf. Mm-hmm. So being able to tell the main topic of a page is something that's really important. And so we use a combination of machine learning and human inputs to try to solve this problem for a really wide range of topics and in a large number of languages.
So when you say human inputs, does that be like annotated text or something? You would have these different annotations like a knowledge graph or something like that you use?
Yeah, some of our learning algorithms can use unlabeled data, just learning from the occurrence patterns of words in just raw text. But a lot of the other ones do need these human labels. So we actually work with a linguist team that works to define what the categories are and train human raters to label data into those categories. Oh. And you know, so it's a combination of the machines doing work and humans providing guidance.
So that seems pretty labor intensive to have the human annotation aspect of that. Is that a large part of where maybe error comes in when you come to like, if you have this machine learning algorithm and you have a little bit of noise and the thing isn't categorized correctly? Is that a fault of algorithms or human error in putting the annotations?
Much more often it's the algorithms. I mean, humans are pretty good at making these judgments. What is the category of this page? Mm-hmm. But then when we try to generalize, you get some new words. You know, we had some example recently where it was a headline saying, new software update turns smartphones into paperweights. And that's easy for a human to understand. This is about smartphones. But our algorithm picked up on paperweights and said, oh, this is antiques and collectibles.
Right. So we understand context much better.
Yeah.
And that's something, and is that something in like machine learning that's one of the goals is to teach context as well?
Yeah. I mean, we try to use context. That's kind of one of our main things we try to do. So if I'm on a web page reading about statistical modeling, I really shouldn't get an ad that says become a fashion model. And we do a pretty decent job at that, but it definitely does fall short sometimes, especially in those cases where it's a metaphor going on. Right. You know, there's still a lot of work to do to get computers up to anywhere near a human level of understanding just general language.
Right. Now you sit here in the Los Angeles office, but you didn't start here. You started up in Mountain View, is that true?
That's true. Yeah, I started working in Mountain View, spent about a year there. My wife got a job in the Los Angeles area, and it was really nice that I was able to transfer to Google's Los Angeles office. At that time, it was actually in the city of Santa Monica, just a couple miles from here. Since then, we've moved just a couple miles down the road here into Venice Beach area, which is part of Los Angeles.
Right.
And yeah, I mean, it's been great coming to this office. For one thing, I got to work on the Signals team, which is really right up my alley in terms of my interests in machine learning and text understanding. And also, it's a great location, and it's a much more manageable size of office compared to Google Mountain View. I mean, that's a big, you know, over 10,000 employees there. Here, it's a matter of hundreds of employees, much more manageable.
So you like the smaller office feel?
Yeah. I mean, it's big enough that we have a diversity of projects, but it's small enough that you really get to know people.
Well, so what's one thing about the LA office, other than the size being much smaller, that people may not know that you would think is interesting? Like, what's your favorite thing?
Well, one thing I think is really cool, which I like to show visitors when they come to visit me, is we have this 3-story tall binocular sculpture in the front of the building, and you can actually go inside that from inside.
I didn't know that. Yeah.
Yeah, yeah. There's little sort of tiny conference rooms.
We're going to take a
inside the
5-minute break.
lenses.
No, I'm just kidding.
Yeah, if you're really nice, I'll take you there afterwards.
No, I knew that was designed by Frank Gehry, right?
Yeah.
But I didn't know you could go inside it. That's really cool.
That's awesome.
Is there anything in there?
Well, the funny thing is, there's these kind of hanging light bulb chandeliers, like a big giant light bulb with light inside. So I don't really know why they chose to do that. It made sense at the time.
Also, you're really close to the beach as well. Do you have a lot of people who head out at lunch or just take a break and go swimming or go surfing? And
there's
come back?
beach volleyball. I know one guy here who always bikes in and takes a dip in the ocean before work. It's kind of
great.
too cold for me, but I do like jogging along the beach walk there.
Yeah.
It's nice. You don't have to stop at any crosswalks, and you don't get bored running along Venice Beach. There's always
There's always
see.
something to see.
Yeah.
Well, really cool. Really cool. Well, we're gonna field some questions from the audience. You want to stick around and see if any you might want to answer too?
I'll stick around. Yeah.
All right. So, this is a very non-programmatical question, but it's interesting because I wondered what they were too. So Aditya asks, what are they wearing headphones for? Are they hearing music, or are they wearing it just to avoid external noise?
Yeah, I think it's probably a little bit of both to avoid any distractions, although the room's pretty quiet in there. We don't have people coming in or out. We've sort of blocked off the room from we don't have just people walking in so much. But avoid distractions. They're also, a lot of them are probably listening to music, also just to help block things out. I think before the contest we said, you can use any streaming websites you like. They don't have general internet access, but we said we'll open up. If you want to use Google Music or anything else, then that's fine. And a lot of people bring their own music. Yeah, I used to listen to. I'd put on sort of a whole album or a soundtrack of a movie or something where I had some. I would get used to having some sense of the length of time that's passed by sort of where we were in the album. But yeah.
This one is actually interesting. I think I forgot to cover this earlier, but one of the questions from Katarina Urban is, are the contestants allowed to use the internet?
Oh, right. Yeah, no,
Yeah.
They're not. Although in setup time they can, they can access whatever they like and download or install whatever editors they want to use. Although we can do that for them as well. Public domain code libraries, I think they can use. There's some rules around that, but during the contest, no internet access. Otherwise, there could be a team of people back home sort of sending them the answer, all working on, a few people working on each problem, so that wouldn't be any good, but yeah.
So Brian, have you had a chance to look at any of these problems? How did you think you would do it if you were sitting in that room with them?
Oh gosh, I actually tuned into the live stream earlier and saw you and Bart explaining the Kelly's allergy problem. And it definitely gets challenging when you get to these large numbers and trying to do something that's much smarter and more efficient than the basic solution or even the dynamic programming solution. So I think it would definitely be a challenge for me to make progress on these problems with a time limit especially.
Yeah. Well, now, what's your background? So you work in machine learning things now. So your educational background and were you always interested in machine learning?
I've been interested in machine learning really for a long time, I'd say since the end of high school even. And I went to Stanford for my undergraduate degree, and I majored in this field called symbolic systems, which is this major they have there that combines computer science with some linguistics and psychology and even philosophy.
Oh, interesting, yeah.
Talking about information processing in both humans and machines. And then I went and did a PhD focusing in artificial intelligence and machine learning. Mm-hmm. So I've been doing this for
You've been
a while.
having interest for a long time
Yeah,
in this,
yeah. And it's great to be able to put it to practical use here at Google.
I think that's one of the really interesting things about it is you can really work on applicable problems with that kind of background. Well, once again, I know you're a very busy person. We appreciate you coming to the live stream and sharing what you do with our audience.
Yeah, it's been great talking with you.
Thanks very much.
I think next we're going to go and we're going to check out the next set of contestants. Earlier in the live stream, we went over the first 6 contestants, including Mystic, last year's champion. And now we've got the next 6 or 7, if we can bring those slides up. Perfect. So you want to go ahead, Jim?
First, Yegor Kulikov from Russia. He's a software engineer at Yandex. He won the Top Coder Open 2 years ago, and he's a former CodeJam champion.
Oh, returning champion. 2010.
Yeah, so good to see him here again. We do get a lot of the same people reaching the finals of this competition and other competitions because it's they're testing the same skills. There's not huge amounts of luck involved. He's currently in 15th at the moment, and of course he had that mistake earlier on problem B where he ran out of time on the large input, but I'm sure he'll recover from that and be doing well.
And as you said, that was a small point value problem, and there are ones that are much larger, so he could make up from that?
Yeah, he's working on some of the more difficult problems
Okay.
now, so he should be able to catch up.
Next up, we have, and I love this handle, Eat More, I can relate, Yevgeny Kapun, I believe. He's from Russia. He's another student. And this is his 4th time in the Code Jam finals. And so, John, do you know if it's been consecutive years, 4 times in a row, or?
No, I'm not too sure, actually. But,
okay. Well, 4 times in the finals is no small achievement.
Must be almost consecutive if he's still a student.
Well, hey, that's true.
Obviously. So people under 18 can enter the Code Jam, but we're only allowed to bring people who are 18 or older to the final. So that must be 4 years since he's turned 18.
Next up, who do we have? We have Fao, I guess is how you pronounce his handle. Fernando Fonseca. He's from Brazil.
That's right. He's a student at ITA, and he usually listens to video game tracks in an infinite loop when competing.
So that answers that question earlier. This individual is listening to music.
Yeah, so I guess he must have his headphones on, listening to that.
Now, next we have a name I have heard, Gennady Korotkovich.
Gennady Korotkovich, yeah. So he's...
no, it's Vlasek,
no,
sorry.
that's not who's next. Okay.
Yeah, that was my fault. I skipped ahead. Sorry, Vlasek. This is Philip Vlasek from the Czech Republic. He's also a student. Traveling and sports are his passion, other than coding. And then Gennady is next. Now, this is a name I have heard for a while. If we can get Gennady's slide up. Well, let's just talk about Gennady until that comes up.
We're stuck there. Yeah,
what do you know about him? Because you've
Yeah, so we've been pretty excited to have Gennady here for the final. He's actually qualified before, as I said, but he was under 18, so he wasn't able to come. I think this is the first year he's been able to come to the final. And he's had a long history, if you can believe it, even though he's only, I think, 19 or 20 of winning programming competitions. He has 6 gold medals from the International Olympiad in Informatics.
now, what is that?
That is sort of a high school level
coding competition?
programming competition,
Okay.
but it's very difficult problems even though it's high school level. He also has 1 silver medal on top of that, so he went to that competition 7 times. He was first place 3 of those times, and 1 time with a perfect score. The scoring's a little different in the IOI, where you can get partial points for mostly getting a problem right, so that's a really impressive achievement. He also won the Facebook Hacker Cup this year. He was on the winning team of the ACM competition last year. That's a college level competition. He's won the IPSC, he's won the Yandex competition, he's won the Top Coder High School division, and 4th place last year in the Top Coder Open. So
he knows a little bit about programming, just a smidge.
You could say that.
Yeah.
So, he's currently ranked, I think, 7th on the scoreboard.
That kind of ability makes me feel bad for myself. Well, that's great. We wish Gennady all the best of luck. Our next up, we have, I'm going to let you take this name, Ivan, I know.
Ivan Popolishev.
Very well done.
So he's a game author. So he has his own game company of Metroid games. I think they're working on browser-based, massively multiplayer online games, if I'm right about what that company is. He also created the free game Bombermine.com. I was playing that earlier. It's a lot of fun. It's based on one of my favorite games, Bomberman, but it's over the internet. There's just a massive number of players in each game, and you can just join at any time and go around throwing bombs at people and blowing them up. So yeah, obviously a keen interest in programming computer games, and he's done very well to get here too.
And last up from Japan is Haas Lyric, Katsuhiro Hosaka, a student at the University of Tokyo. And composing music and enjoying playing shogi, Japanese chess. I'm not familiar with Japanese chess. Do you know?
I'm familiar with it, but I'm not any good at it.
How is it different than the chess most people are familiar with?
Oh, well, there's a different set of pieces and they move in different ways and everything, yeah. But board games seems to be a common theme in the interests of computer programming competition enthusiasts. Last night when all the competitors were relaxing at the hotel, we got out some board games that we'd brought, and yeah, there were a lot of games being played there just for everyone to relax.
Yeah. Well, that's the next 6. We'll be back in a few. We have actually a couple things coming up. At 2:30, we have an interview with the Chrome team with Rachel Blum and James Hawkins. We're going to have some more audience questions, of course, and we're going to introduce the next set of contestants. I think it will be up to contestant 18 at that point. So stay tuned. We'll be back at 2:30, and we have those interviews.
Yep, so we'll go back to the competition room, and of course you can watch the scoreboard as well. There should be a link there at the YouTube feed, and so we'll be back with you soon.
Welcome back. Sitting next to us are Rachel Bloom and James Hawkins. You guys are on the Chrome team, and you sit in the Los Angeles office. Is that correct?
That's right. Yeah.
So why don't we just start very simply and have each of you give us a little bit of your background and how you ended up here at Google and what you do on the Chrome team.
Shall I start?
Yeah, absolutely.
Okay. I went to school at University of North Texas. I did a lot of open source work on the Wine project that lets you run Windows applications and other operating systems. And through that, was able to parlay that into an internship where I also worked on Wine in the Santa Monica office here a couple years ago. And I did 2 internships and then converted on the second internship. And once school was done, came out here, moved out here full time, and have been working on the Chrome team ever since.
So now why Chrome? So your background is in open source. Did you know you wanted to work on Chrome from the beginning, or is that something you made a choice?
No choice.
Okay.
It worked out fortuitously. I love working on Chrome, and I couldn't have asked for a better project to start out on. It happens to be, when you're getting hired from school, we're generalists, and we hire generalists, so we should be able to be successful on a wide range of topics and projects. And the manager that I worked with on my internship had just got it started on the Linux port of Chrome at the time, which was brand new. So Chrome had been launched on Windows for a couple of months at the time, and we were working on the Mac and Linux ports. And so that was the very first thing I did was worked with the team of engineers here and in San Francisco to bring up the Linux implementation of Chrome.
Okay, so you work on the front end things of Chrome now, or the back end things? Tell me about what.
Right. I used to a couple of years ago, and that involves what Rachel will actually describe about the front end work. The things that I work on now are actually on the Chrome platform, and specifically, we work on Chrome apps for Google properties. So Chrome OS and Chrome on other platforms has a relatively new platform, Chrome platform, that's analogous to Android apps and iOS apps. So we have Chrome apps now.
Okay.
And what these do is it's a layer that sits on top of the web that gives you access to deeper APIs, a little bit more access to the system because we have more protections and security. So we have a sandbox, and given that sandbox and those protections, we're able to have deeper access to the system. So that's Chrome apps in a nutshell. And what my team does is implement those Chrome apps for Google properties that we think are really important to have out there that really makes sense as standalone native-esque apps. It just happens to be web technology that we use to implement it. For example, we launched a few years ago Google Plus Photos as a Chrome app. And just recently we launched Play Movies, which on Chrome OS you can pin movies for offline playback and all that good stuff.
Cool. Mm-hmm. Now what about you, Rachel?
So I started at the RWTH Aachen in Germany.
Okay.
And from there I moved on into several jobs. There is not a theme because I've always been a generalist. It was a lot of interesting things. One of the first CD recorders, a very tiny role in the European Space Project. And at some point I just slid into video games. I spent about, let's say 15 years or so in video games. It was really interesting. And then there was an opportunity to work for Google, and that was kind of interesting to me, so I switched.
Well, I'm interested personally in video games. It says here that you have a background. You worked on World of Warcraft.
Yes, I did.
That is amazing. So is that in relation to what you did for World of Warcraft to what you do now?
It's actually fairly similar, weirdly enough, because for World of Warcraft, I was working on software that sort of supports World of Warcraft. If you install World of Warcraft and by now it streams things in nicely instead of asking you to apply 15 updates, that would have been my team. Mm-hmm. And so it's essentially, it was already desktop applications. So that sort of translates into what we're doing in Chrome.
Interesting. I think if you were to query most people and say, what's the connection between Chrome and World of Warcraft? Most people would not know. So that's a great information.
Yeah, so what do you like about working in the Los Angeles office?
I think one of the biggest perks, and we get asked this question all the time, but the biggest perk, and this applies I think to most people across Google in all the offices, is really the caliber of people that you work with day in and day out. You don't find that everywhere, and when you've experienced working at different places and working with different types of people, whether that's in a job or at school or doing open source work, et cetera, it's above and beyond. So it's really great to be able to come in and you have this tremendous respect and you're given that respect back it's a wonderful feeling, and you just can accomplish so much. It's really limitless what you can accomplish.
And I guess working on Chrome team, there's a lot of different parts to the Chrome browser. There's engineers and there's designers and things like that. So I guess there's a range of skills in the people you work with that must be interesting.
Absolutely, and you know, this was my first real big job, and so there's functions in a company, you know, like Google that I was totally unaware that existed, like product management, UX, user research, all these things which come together that are critical functions, not just engineering. And even outside of products that we do that are software related, like sales, for example, all of these people are so crucial to the success of the company, and it's sort of eye-opening, like how important every role is, and there's so many of them.
So how about difficult algorithmic challenges? Are there any of those in Chrome? Are there any parts of the browser that need really efficient algorithms to make a good product?
I think it's really true for all parts of the browser. You always want to pick things that, you know, work efficiently for whatever you're working on right now. It's not like there's this one crown jewel part of Chrome and you go in there and that's the secret part. There are lots of different parts and they all require a lot of thought going in there.
And I think it gets to a point at the complexity of Chrome where it goes beyond just algorithms, and it's more of really creative thinking in terms of the problems that you have to solve, and not just going from n-square to linear, for example. But there's an effort going on to really speed up rendering, and that's always been a core focus of the Chrome browser, but even more so when we're turning to the mobile world and saying, what's the browser performance like on mobile, on iOS and Android? Can we make that faster given the relatively limited constraints on some devices, but it's not like a desktop, you know. As much as hardware is progressing, there's still a lot of challenges. When we went to mobile, we kind of took a step back in terms of the performance that we can get. So we had to take a fresh look at performance and say we have to be as quick, as speedy as we are on the desktop on mobile, and that requires very creative thinking.
Wow, that's fascinating. Sounds like there's a lot of interesting challenges in working on Chrome.
Oh yeah.
Yeah, I'm sure a lot of the 26 people we have here would be interested in working on that sort of thing. Maybe we can convince some of them to take it on.
One could hope.
Absolutely.
I'd like to talk to them. Yeah.
And this ties into the question that Bart fielded about like how related are these kind of problems to the kind of work we do, not in the specific of the problem, but having to code very efficiently and having to minimize runtime and things like that. I think that's really interesting, and that's, I don't know, it's fascinating.
Absolutely.
Yeah, I mean, I think, you know, they're certainly related, because whatever you do as a software engineer, ultimately, it's about looking at a tricky problem, taking it apart into smaller pieces, and solving this, finding an answer to this.
So now I have a final kind of fun question for you guys, and we asked our previous interviewee, what is one thing about the LAX office that people may not know about that you really enjoy? And it's not the binoculars, we already got that one. Yeah,
Okay.
it's going to make it a little tough.
There's really a lot of things. I would say the people, but I would hope people know that, you know, Google is a fun place to work at. For me, what really was surprising when I joined Google LAX specifically was the amount of, you know, care about the community. People are volunteering for Meals on Wheels to help out with local schools. You know, there's a lot of volunteering efforts going on in addition to what everybody is doing at work, and that really spoke to me, because it means, you know, we don't just care about our job getting done and then going home.
Yeah, I absolutely agree. That's the exact same answer for me. And we do reach out a lot to the community and say, we're here and we want to make a positive impact, and how can we do that? So one of the things that we do in our community affairs is there's STEM, science, technology, engineering, mathematics, and we try to fund and give grants to schools and organizations which promote that area of society. And there are some other areas that are not just STEM related, though. For example, there's an organization called A Window Between Worlds, and they do art therapy for domestic abuse folks that have been a part of domestic abuse, and also homeless people around the area. And in addition to giving us a grant, they have an office right down the street, but it's really small. And they asked us if we could host a meeting for them, because they had a big announcement that they wanted to make. And we run the numbers and we say, absolutely, this is definitely worth it. Let's host them. We'll put this on and give them that space that they can do their big announcement. That's really positive for them. So just we're always on the lookout. We're always looking for organizations that we can sponsor and help out in any way that we can. So it's important to me. I think that's a big part of who I am, which is making a positive difference in the community. And we're given the time. I can spend an hour a week at this meeting where we talk about these issues, and that is totally okay.
So you feel like what's important to you is that you feel like Google is being a part of this community and giving you the time to give back.
Yes, definitely. So much time.
Great. Well, thank you so much for stopping by and giving us your time. And if you were not as familiar with CodeJam, we invite you to watch the live stream for the rest of the
Definitely.
day.
Absolutely.
But thank you for stopping by.
Thank you.
Thank you.
So I think
we'll cut back to the competition room, and we'll be back in a few minutes. We can do a rundown of the scoreboard and let you know how everyone's going.
So John, we've had some developments with the scoreboard.
Yeah, so Igor Kulikov has recovered from his earlier wrong answer and he's now winning on 74 points. He's finished problems A through D.
No attempts at problem E or F? He's probably working on them now.
Yeah, he has problem E, allergy testing, that we were just talking about earlier. He has that open and he's working on it. In second place, we have Mystic, our returning champion. He's on 73 points. He's solved the small of allergy testing, but hasn't solved the large of problem D. So he has one less point for that. Eat More is in third, Romka is in fourth, Vepifanov is in fifth, and Gennady and Hoslyrik are both on 57 points in sixth and seventh.
But just as a reminder, these points are assuming they got the large input correct.
That's right. So all of these top scores now involve some of the large submissions on some of the large inputs.
Which may be wrong.
They might be wrong, so they won't know until after the contest when we do the announcements whether or not they've really got those points. So they have to keep that in mind when they're strategizing about what to work on. And so the people who might be ending up with the same score but haven't got there yet might be thinking that they'll take a bit more time and test their submissions more thoroughly, so that they're just sort of more likely to have them correct and hope to beat the people who got to those points first by having more correct answers.
Now, if I can ask a potentially stupid question, if you look at Igor, problem D, he has 2 wrong tries, but also a submission for large.
Yeah, so I guess his solution to that's the problem paradox sort. We haven't explained that one.
We haven't
yet,
explained that. But
yeah,
my assumption is that you would wait to see if your small input was correct before you'd submit a large.
Yeah, so I think we enforce that. You can't attempt the large until you've got a correct small submission. But yeah, that must be it might be a little bit worrying for him that he had 2 wrong attempts at the small input. So he had a couple of bugs there. So he has to sort of be confident that he'd found the last bug before attempting the large input. But yeah, hopefully he thought about it for long enough. He submitted the large actually not long after he submitted the small. In fact, only 4 minutes. So he kind of, after he got it right on the small, he didn't spend a lot of time doing further testing. He just went straight to the large and submitted it. So I guess he was either quite sure that he's got it right, or he's trying to get himself more time to work on problem E and F. There is only 1 hour and 42 minutes, and E and F are very difficult problems. We have no correct submissions on the large for either of those, and we only have 1 for the small of problem F. So he probably wants to make sure he has as much time as possible to try and get some correct submissions for them.
Now, related to scoring, we have a question from the audience, actually from Roman Andreev. His question is, why is there no column in the scoreboard that shows the number of points that contestants will get in the worst case?
Yeah, I guess we could add a feature that says, here is the minimum they can get. So that would be the sum of the points that they've gotten for small input submissions, because they definitely have those points because we test them immediately and tell them whether they have the right answer. But,
I think this creates more suspense, to be honest.
Yeah, we could do that. I mean, the competitors are probably doing those calculations in their head when they're figuring out strategy. Yeah.
Now, do you think, when it goes to strategy, I mean, is this something that, are they spending any amount of time, significant amount of time, looking at what other people have submitted, or are they just focused on getting as much done now?
Mostly, I think while they're solving a problem, you're focused on the problem that you're currently solving, keeping that in your head, writing your solution, and then when you finish a problem, then you go back to a check of the scoreboard when figuring out where to go next. So you're looking at where you sit in the scoreboard, whether you're, how many points behind you are, whether other people have got to the same points but faster, and have a look at how people are going on the other problems. If you didn't know yet how to solve E or F, even for the small input, if you hadn't spent time thinking about it, then the fact that I think it's 8 people now have solved E and small, and only 1 person has solved F small would give you a hint that E might be a bit easier. On the other hand, maybe that's just the order people have tried things.
All right, well, speaking of contestants, I think it's time to introduce our next set of contestants. We can get those slides up. We can introduce, I guess, the next 7. And first up is Isia Lian from China. He's a software engineer at NetEase, and This is an interesting fun fact. He writes classical Chinese poetry.
That's interesting.
Yeah.
Maybe we'll have to get him to present some of that later on.
I think that should happen tonight.
Get him to write an ode to the winner. That could be interesting. But
I doubt he's writing poetry right now. He's probably focused on a problem. But
I think at NetEase he is working on their computer games division. So that's another person in gaming.
another game. Next up is the handle I'm pronouncing correct? Martin Smoo?
Yeah, I'm not sure about the handle.
Marcin
yeah,
Smoo?
Martin
Yeah.
Smulovich.
Polish, student at the University of Warsaw, and he has placed 3rd place in the Facebook Hacker Cup in 2013. So he's
that's pretty good. That means he beat me.
Where did you place?
I managed to make the final and then did not do all that well. I think 21st or something, but that's all right.
You had a bad day.
Oh, thanks. I'll blame it.
Next up, we have MK Alien. Mikhail Kolopayev?
Kolopayev.
From Russia and a software engineer at Yandex, with his interest being reading, origami, and juggling.
Yeah, so it's another Yandex engineer.
I think that's the first juggling I've seen. Ramka, I'll let you take this name.
Roman Udovichenko.
Oh, better than I could do.
Another engineer from Belarus,
And
also at
from
Yandex. And the fun fact he told us about was apparently he has a small dent in his head. I don't know what.
Now, John, do you think that small dent helps him program better?
I don't know.
Because if that would help, find me a hammer. No,
probably a
no,
bit
of course
extreme,
not. It is
yeah.
extreme, but that's I think the most interesting fun fact we've gotten so far.
Yeah, it's certainly not holding him back.
No. Next we have is this
Roman Kristov from Bulgaria. So he's a student at MIT. He told us his favorite coding language is Go. I don't know if he's using Go for the competition today. He may just be a fan of the language for particular applications, but sometimes these people know multiple languages and choose the one they think is most suited for programming competitions when they're competing. That's developed, Go is obviously Google's programming language. It's partly developed in Sydney, actually,
where you sit.
Where I am,
yeah. Next up we have Iwi Takuya Akiba from Japan, another student from the University of Tokyo. And this is his 3rd time in the Code Jam finals.
That's right. He's taking a break there for a snack.
Much needed nutritional brain power.
Important to have enough sugar to keep going. He's staring at he's drawn a diagram there on paper. So that's a good time to while not typing, take a break to eat.
I find remarkable about when we're looking in the room here is that none of these competitors seem stressed at all. They seem like they're really focused, but none of them seem stressed.
Yeah, well, I guess a skill you have to have is to sort of remain
cool under pressure.
Calm, cool under pressure, and basically try and get in the same frame of mind you would have if you're just solving interesting problems for yourself at home. So when these people are practicing, when they're training up for a competition, they'll be at home picking problems off the internet from past contests or from collections of interesting problems and just solving them. And I think you have to just get in the same frame of mind when you're competing.
Easier said than done for me. But yeah, I'm impressed by that. And next up we have Sheik Tingwei Chen from Taiwan, another student. And we don't know much about him. He seems to be a bit of a mystery.
An enigma. There he is.
There he is.
Typing away. Not sure what problem he's working on. We can actually look that up here.
So there's another question we got from Aman Mittal, I believe. And is there an editor that the finalists are using to code, or are you allowed to use any editor that you want?
Yeah, they're allowed to choose whatever editor they like. We let them install whatever takes their fancy. I think I saw some people using GVim earlier in the shots of the room.
What's your favorite?
I use GVim, actually.
Okay.
That's how I spotted it.
Okay.
But yeah, it's up to them, and they can configure them with any macros or shortcuts or whatever they like to just be able to type in their solutions faster. Obviously, the most important thing is thinking of the answer at all, and shortcuts just help you a little bit.
I think this question is definitely suited for you. This comes from Michael Moffat. Out of curiosity, how often, if ever, do the CodeJam questions turn out to be NP hard?
That sometimes happens.
Well, first,
turn out to be NP hard makes it sound like we would do it accidentally. We usually know how hard these problems are to solve. If any of them were NP hard, we would.
Well, first off, explain to people like me NP hard.
Right. So yeah, it's a concept that describes a set of problems that we believe are very difficult to solve with an efficient algorithm where efficient in this case means something that takes at most a polynomial number of steps based on the input size.
Okay.
So if the input is a million numbers, then it might take a million squared or a million to the power of 1.5, something that's polynomial rather than exponential. But sometimes we do use these sort of problems on CodeJam for much smaller inputs, so that even though they're technically NP hard, we're asking them these questions in ranges of input where it is feasible. More often though, actually, NP hard problems might be the inspiration for a different problem we write that's where we take an NP hard problem and we add some additional constraints. So we had a problem that was a satisfiability problem, but had an additional constraint that allowed a polynomial time solution. So that was, I think, a problem called milkshakes from an earlier year. So yeah, not very often are they actually NP hard problems, but this set of very difficult problems often forms an inspiration for making something interesting that's more approachable.
Well, joining us, and you might know this individual, John, so why don't you introduce?
Certainly do. This is Igor Naverniuk, also known as Abednego. This is a handle in programming competitions. We were both up late last night finishing off the problem set, to be honest, putting in the final touches. So you're going to take us through the problem symmetric trees.
All right. Can we show it?
Yeah, they're going to switch to that, but you can just
We
look
have
at this.
some slides.
Yeah, if we can go to the slides when you get a chance. Perfect.
All right, so this problem is about making a tree symmetric. So I should explain what a tree is. In computer science, a tree is one of these things that you can see on the picture. It is a collection of nodes, and in this case, nodes have colors, and links. And links are straight lines or straight edges that connect two nodes, and you can think of them as pieces of rubber that can stretch to any length you want. So, and you can also rotate nodes around each other. And the question is, given such a tree, can you place it in a plane in such a way that has this symmetric shape that you see in this example? And this symmetric shape around a line. So you have to have a left side matched to the right side. So here's an example of a symmetric placement. You can see that the red node and the green node are on a line, so they're symmetric to themselves. And nodes 3 and 4 are on opposite sides of the line. But to be symmetric, they have to match two conditions. They have to have the same color, and they have to have the same connectivity to something on the line. So 3 connects to 2, 4 connects to 2, so it looks symmetric. And on the right, the tree is not symmetric because the colors are different between nodes 3 and 4. So here's what the input looks like. Just as before in the other two problems, we have the number of test cases. So they have to solve this problem many, many times over. And in this case, they just need to say yes or no, symmetric or not symmetric. They don't need to produce the actual arrangement. And for the small data set, the number of nodes is going to be up to 12. And for the large one, it's up to 10 to the power 4. And they're specified as, so you can see there are 3 test cases. And the first test case, there are 4 nodes.
The second and third test case are not shown, just for clarification.
All right.
Yeah.
So you need to be given 2 pieces of information. One is what is the color of each node, so in this case it is RGBB. And next you need to be given the connectivity information, which node connects to which other node. So you don't know the arrangement to begin with, but it sort of doesn't matter because you need to produce a new arrangement anyway.
So I guess one of the things I've found in these problems is in these examples, it seems like, okay, in principle, this is very, a simple problem. But then when you start dealing with these very large numbers.
Right, of course, as in every other problem, things get quickly out of hand, which is why we need computers. So you're not going to be able to solve this case by hand unless you want to spend your lifetime. So that's the difficulty of the problem.
I don't know. I think you and Bartholomew were in here earlier, and you were actually looking like, oh, wait, does this loop around? Hold on. You were almost doing it by eye.
I was just impressed that you were able to produce this picture. It looks pretty pretty.
But
So this is the third hardest problem. We didn't set the constraints for this problem too large. I think we said n is at most 10,000 in the slide. I think we lowered it down to 6,000. So that means that a solution that takes running time about the square of the size of the graph is going to be easily fast enough. So that's definitely, we don't think it's NP hard. Did I flub the explanation of NP hard before? I think it's a set of problems where we believe them not to be solvable in polynomials.
So I would say the main difficulty of this problem is that in most problems you have some fixed number of solutions you can enumerate. You could say, well, I want to find some ordering of something. So I can order them in n factorial ways. That's how many orderings there are. If you're talking about placing trees onto a sheet of paper in symmetric or not symmetric ways, then there's infinitely many ways of placing that. I mean, you could move it a little bit a little bit up, a little bit down, a little stretch it a little more. There's as many of them. So you cannot enumerate all the possible ways of doing that unless you come up with some mental representation of what a certain class of placements looks like, and some reason why you would think that they're all the same, really, essentially. Because if you think about it, if you place a tree in a symmetric way and then you move every node up a little bit, it doesn't really make any difference, right? But how do you formalize that, and how do you convince yourself that this is actually, that your mental representation of all the possible placements is really the complete one that covers all the possible placements?
So they have to understand the problem well enough, understand what's going on, such that they can think of a way to sort of represent an answer that would be realizable as a way they can draw it flat. So so we can't try every possibility, but I think some of the easy submissions probably try every possible matching of nodes on the left to nodes on the right, and so the constraints are very small for the small inputs. So that sort of.
Would I be wrong in thinking that in a sense this is asking for a proof? I mean, if given these nodes and these edges, that this falls with, if you have these criteria, yes, this is symmetric.
So it's certainly one of those mathematical problems, at least on the surface. So there's some mathematical structure you need to discover. But in this problem in particular, after you do that, you still have to figure out an algorithm and how to implement that efficiently once you discover the structure. So that's kind of it's doubly hard. It's math hard and it's programming hard.
How nice of you guys.
Anytime.
So a lot of people have solved this problem. 15 have solved the small. 13 people have made attempts at the large input, although we don't know yet whether they've got it right. So it's fairly approachable. Most of the people in the top ranks have solved that one. Trees or graphs in general do come up a lot in computer science, and so they come up a lot in competition problems. And they may have seen similar things to this, maybe computing whether two trees are the same but rearranged might be a problem that's come up before as part of some other problem, but here we've got a bit of a modification of that. They're finding if a tree is sort of similar to itself, if there's some automorphism that makes it symmetric. So,
a fun question just came in. I think it's funny. It's very lighthearted. Jonas Cherovim, I believe. How much IQ is accumulated in the competition room?
I think there may be some correlation between IQ and being able to solve these problems, but I wouldn't say that it's the same thing. Or I don't know. IQ measures how well you do at IQ tests.
Exactly.
Yes. I guess we're measuring how well you do in programming competitions, so that's fair.
Yeah, it's much more important.
It's more useful in some cases.
And this question, we asked it before, but it's on here again. Nilam Kernia, did I already ask that question, I believe? How well yes, I did. How well a random Google software engineer would do.
Oh, no, we didn't ask that. How well would Oh, that's a good question.
It is a good question. I thought I had asked it to the last interviewers.
Yeah, the 3 people we had who were just employees in the Los Angeles office, maybe we should have asked them.
And you have experience with this too. It's how well, if you just took a random set of Google software engineers, how well do you think they'd do in the CodeJam finals?
We do run an internal competition, right?
Right. So that's what we do. We run these problems through an internal competition first to see if anybody can solve them. And we try to make sure that everybody who submits a solution, every Google employee who submits a solution to this problem actually agrees on the answer. And if there's some disagreements, we try to figure out if our test cases are incorrect or if their solutions are incorrect. So we have a pretty good answer to that question. I don't know if we want to share the exact number. And also not everybody competes 100%. In these things. It's less than 100%, okay. But it's more than zero.
There's quite a few wrong answers on problem A, even in the small case. A few people. Well, there's been some wrong answers here today. Lots of wrong tries. I don't know what it is. They're all getting wrong there, but
I think I have an idea because there are 2 ways to have a checkerboard, right? You can have a 0 in the top left or a 1 in the top left. So it's very easy to assume that it's going to be a 0 and forget that you also have the other kind of case where it's 1 0 1 0 instead of 0 1 0 1.
Right.
Possibly, yeah. But yeah, we don't make every employee enter these things. But yeah, I think I don't know. Our interview questions are often fairly algorithmic in nature. We throw a problem at someone and give them sort of 45 minutes to explain an answer.
Yes, doing well in these competitions certainly prepares somebody for interview questions, or at least some of the interview questions. Because some interview questions don't really fit nicely into this format. So especially if we're asking somebody to come up with some design of how to connect certain servers to achieve some result, it's not something we can turn into a programming problem. It's more of a design problem.
Right. Yeah.
So far, we've been, you've been talking to interviewees. We've been going, showing the contestants. We've been showing shots of the competition room. Igor, what's it like in the judging room? What goes on in there?
We're watching the scoreboard. Whenever somebody submits a solution, we try to look at it and see if it's some clever new algorithm we haven't seen before, or if it matches some of the solutions we've had already. We also were able to see who is looking at which problem. So Hans Lyrik, for example, went with his patented strategy of starting with the hardest problem first. And then if you look at the scoreboard, he actually managed to submit the small for problems F and problem E within 2 minutes of each other, which is really interesting because there's no way he could have solved problem E small in 2 minutes. So he must have been working on both of them simultaneously for a while and then decided to submit both of them at the same time. I don't know why he's doing that, but that's an interesting strategy.
Possibly he had, maybe he's running his own tests and he left, had a self-testing program running on problem F and sort of left that running while looking at problem E, and after he'd submitted that, came back, hadn't noticed any problems, and decided to send it in, maybe. But,
and then 4 minutes later, he submitted D small. So he's sticking to the strategy.
And working in parallel. And
he's really batched up a few things to submit at once. Well, the way the tie-breaking works is based on the time at which you reached your eventual score. So that is this, which I think is good. That makes this a valid strategy. It's not sort of holding up. We don't sum the submission times of each problem separately. So yeah, it's certainly a good strategy. He's in 8th place at the moment.
And he's the only one with the solution to problem F, F small.
That's right. And so he hasn't even attempted C yet, which a lot of people have solved. So we can sort of expect he'll pick up those 25 points. And if he does that, that would put him in the lead at the moment.
It's true.
All right. So I think what we're going to do is we're going to cut back to the competition room. And we will be returning at 3:45, and we'll have the last set of contestants and answer some more questions and check in on any developments on the scoreboard.
Yep. And we're still watching the final of the 2014 Google Code Jam. You can see the competition room there.
And we've got just about an hour left of time remaining, correct?
That's right, 1 hour, 4 minutes.
So what's the scoreboard looking like now?
So at the moment, Gennadi's taken first place. He's on 101 points.
Wow, so he was 6 and he's jumped up to first.
That's right, so he solved the small and the large for problems A through D. And early in the competition, he solved the small input for problem E. Second place on the same number of points, 101, but 2 minutes slower in total time is Eatmore. He solved the same set of problems. And there's a gap of 12 down to MK Alien, who hasn't solved problem B, the large from problem B, so that's why he's 12 points behind.
So it's safe to assume that Gennady is pouring all his efforts into the large of problem E and problem F.
Yeah, he is currently looking at at allergy testing still, so that's problem E. So he's already solved the small, so he has a reasonable handle on the mathematics of it and how it works.
So he's trying to figure out how to solve it when the number of foods can be 10 to the 15.
Yeah, there is a big jump in difficulty from the small to the large, so he's probably improving his solution, trying to get it to work for those large cases. Let's go back to the room, see if we can see what he's doing, maybe.
If we can get a shot of Gennady, that would be great.
Probably pass him later, but yeah, so he's probably either working hard with pen and paper, trying to figure out an algorithm that can solve the large input, or maybe he's already working on it. But yeah, not too far behind in the scoreboards, 7K plus on 83 points. He is currently working on symmetric trees, problem C that we were talking about earlier.
With Igor, yeah.
Yeah, that's right. He solved the small input not that long ago, about 15 minutes ago. He's still looking at that problem, so I guess he's working on improving his solution so it'll work for the large. Actually, I think he might have just got it. Yeah, so now there's 2 people on 89 points each in 3rd and 4th place. Only 5 minutes separate them. So they'll now have to decide whether to start working on, well, I have a few options, the large of problem B or E, which they've already solved the small input for, or they might start on problem F. Problem F, the small input for problem F is actually worth more than the large input of problem B. So if they notice that, they may be planning on just skipping the large of problem B and trying to jump ahead by getting that more valuable submission done.
So I'm going to take this opportunity to just answer another question. You answered it earlier in this live stream, but from Aaron Gu, what age should you compete? Should you be to compete in Code Jam? And if I recall correctly, you have to be 13 to compete, but 18 to advance to the finals. Is that correct?
Yeah, that's right. So we often have people who are 13 or over, but not yet 18, enter. Occasionally they even qualify for the finals, but unfortunately they can't come until they enter in a year when they're at least 18. Gennady, I mean, I think that's happened to multiple times. I think maybe 3 times before this year he's qualified.
But couldn't come because
of the final,
age.
but yeah, couldn't come. So yeah, so we're glad he can come this year.
All right, so maybe we should introduce the next set of the participants, our last set of participants, I believe.
That's right, so we have some slides.
We should have some slides of the last 6 that we have not presented, and that'll round out the 26 total competitors in this Code Jam. Up right now we have Kepnu 4, so Valery Filev, hope I pronounced that correctly, from Russia. He's a student and favorite coding language, C++. It seems to be very common.
Yeah, that's right.
And then the next one we have Vipifanov, I believe. Vladislav Vipifanov from Russia, another student. Football, movies, anime, and video games.
Yeah, all pretty common interests we've seen from these people, especially video games. There he is working away. Next is Vladislav Simonenko from Ukraine. He's another software engineer from Facebook.
There's quite a few of those in this year's finals, right?
There's been a few, yeah. I think they're trying to pay us back for because we keep winning the Facebook programming competition. Where is he at the moment?
He's hooded up and he's focused in, yeah.
He's on 58 points. He's in 13th place at the moment. He's had one wrong try at problem E. If he fixes that solution, he'll be able to jump ahead a few places.
All right, up next we have Kawatea.
Yuki Kawata from Japan. So he's a student at the University of Tokyo. We've had a few entrants and I think 2 or 3 finalists from the University of Tokyo. Obviously it's a good place to go for the people who are interested in these sort of things. There he is working away.
Now let me ask you a question, John, and this comes with, you have a lot of international people competing. How carefully do the CodeJam engineers frame the problem statement so that language isn't a problem when you're reading it?
Yeah, so for each problem that we're writing, we have a number of tasks. Someone has to write the problem, someone has to work out the input data. We want several people to solve it, and 2 of the really important tasks are proofreading it, and proofreading it to make sure it's clear to people from other countries, other cultures, or when just English isn't their first language. So we have one proofreader who is a native English speaker and one who is not, and so they make sure that we don't use any idioms that are a bit confusing, or that references to things that people wouldn't understand, or that we don't have really long run-on sentences that are too complicated, because we don't want the challenge here to be understanding the problem. Understanding what the problem is. We want them to know what we're asking. That should be very clear. Then the hard part is figuring out how do you write a program to solve it. So yeah, it's an important part is making sure that they're clear.
It's understandable to all the competitors. Second to last on our competitor list is 7K plus G. Yuju Gu, I believe it's pronounced. It's a student from China, and he is at MIT right now. So
he's another MIT student.
Yeah.
His interests are Go, Mahjong, anime, math, and coding, of course.
And this is interesting. I think this is the first we've seen people interested in the Go programming language, but I'm assuming here he means the game.
Yes, the board game.
The board game, which I always thought was a very interesting game, because that's one of the games that it is very hard to have a computer learn how to play competitively, because there's so many permutations to the game.
It is a very difficult problem. Yeah, you have a 19 by 19 board, and the 2 players can place pieces within that board. So there's a lot of options. So it's difficult to write good computer programs to decide what's the best move. And because I'm not a Go expert, but it's very strategic and takes a lot of expertise for humans to be able to tell even who's doing well on some part of the board.
And it involves pattern recognition too.
In general, yeah. So getting that coded into an algorithm is very difficult. So yeah, it's an interesting field of research.
And our 26th contestant here is Wu Jingkai from China. He's another student at Peking University, and his interests are reading, football, and animation. And there you see him in the corner, working very hard. Do we know which problem he's looking at right now?
He is looking at allergy testing.
Allergy testing.
And he's currently in 24th place, 29 points, but allergy testing is worth a good number of points. So hopefully he'll get that finished in the next 56 minutes remaining. Top 2 positions are still Gennady and Eatmore with 101 points each. Oh, Eatmore's made an attempt at the large input for problem E, allergy testing, but he's run out of time. So possibly his solution, maybe he was not certain whether it would run in time, but thought it had a good chance. It is a problem where it's not easy to figure out the running time of some of the more complex solutions you could try to solve the large cases. Igor and Bart were discussing yesterday how the best solutions worked and what the worst case running time would be, and it's not easy to figure out, although of course you might have a completely different idea for a solution than what we were thinking of. So it's possible he he knew that he wasn't certain to get it right, and he's just sort of taking a bit of a gamble. He's maybe trying to leave himself some time to move on to problem F, and he's taken a bit of a risk there, and unfortunately it hasn't paid off. But yeah, anyway, he's certainly working on problem F now, because that's the only thing he has left to work on, having finished problems A through D and E small. Gennady, let's just take a peek at what problem he has open. He still has allergy testing open, so he's probably working on the large of that. Now, if he solves that, that'll give him 35 more points, which is worth more than the small input for problem F. So if Gennady finishes that and Eatmore finishes problem F small, then Gennady will still win. Of course, both small and large for problem F are worth 64 points, so that would put Eatmore clearly in the lead if he manages to solve that.
Now, while we don't have an animation, can you, one of the problems, paradox sort, is that something you can possibly explain?
Right, so the setup of the problem is that there's a bunch of objects, and we're going to apply an algorithm to find the largest of these objects, except that the comparison is a little strange. So the setup is that there's a person who is going to be offered a sequence of candies, I think is the way we come up with the story to explain the problems. And then we give them to them one at a time, and they take the one that they're holding and the one they've just been handed and figure out which one they like best. But in this problem, we haven't given the person a consistent ranking of everything. They might prefer A to B and prefer B to C, but then prefer C to A. So the ranking doesn't necessarily make sense. What we want to do is, given all of those pairwise preferences, come up with an ordering of what order we're going to give them the objects so that they end up with the one that we want them to end up with.
Gotcha.
So you have to come up, and then you have to find the ordering that is lexicographically minimal, which means sort of if you listed every order in a dictionary, which one would come first. So you have to sort of think about what the structure of one of these permutations of objects would have to look like in order for the right thing to come out as the winner. So you have to, when I was approaching the problem, I sort of drew this as a graph where there are arcs from one object to another if that one is preferred to this object, and then you can sort of think of the progress of handing that person as an object as considering a sequence of edges, and then you can sort of think of embedding a tree in this graph.
Is this another tree problem that can be visualized that way?
Big diagram I have over there of what a tree. There's a tree and then another tree somewhere else, and so they have to. Really, it'll involve a lot of sitting down and thinking about the structure of this graph and what sort of coming up with even a valid algorithm is fairly tricky.
Yeah, because the reason I ask is for the large input for problem D, which I believe is paradox sort. That's the one that's, other than E and F, that has the fewest large inputs of our
Yeah, so
solutions.
the main difference between the small is actually small enough, I think, that they can just try every sequence of these objects and hand them to present them and check if they work and just choose the first one that works. So it's actually fairly easy to get those points. That's why there's only 4 points there. But for the large, they really have to understand the structure of a solution much better, so they can find one efficiently. But it's not too difficult compared to problems E and F to come up with an efficient large solution. Yeah, for the small data set, n is at most 10, and 10 factorial is the number of permutations, just not very large. So that's why pretty much everyone has solved that. Let's go back and have a look at the competition room.
Yeah, as you said before, there's less than an hour now. There's about 45 minutes till the end of the competition, I believe.
That's right. I think we started a little bit late, so there's
51
minutes.
Yep.
That should be enough time to see a few more submissions in the upper ranks, but of course they are very difficult problems. Allergy testing we explained earlier, one of the two hardest. The other problem F, is ARAM. How many people have opened this problem? Only six people have it open. They're currently reading it. It's a quite difficult problem, so it's actually inspired from a video game. And the setup is that at the beginning of this game, you sort of choose one of, well, and I think in the question, one of 1,000 options gets given to you randomly for a character you're going to play in a round of a video game. And you know for each one of those 1,000 characters what the probability is that you'll win the game if that's the one you're given. And you also have an amount of hypothetical money that you're allowed to spend in order to get a repick, a re-roll of which of those N characters you're going to get. And then you accumulate a small amount of that money over time. And so the problem is to try and maximize your chance of winning in a very long series of games. So you have to find the best strategy of, given how much money you have, when should you spend your money to re-roll when a choice isn't very good. And it's a very difficult problem. Even the small, you can't sort of try every possibility, and you can't simulate the game because that number of steps is 10 to the 100 actually, which is the number called to Google. So there are sort of standard techniques for solving these sort of repeated games and trying to find the optimal strategy, but those won't work for this problem because of that very large number, 10 to the 100. So they're going to have to sort of think a bit more deeply about the mathematics of this problem to come up with an algorithm that can solve it. More people looking at pen and paper, drawing some diagrams, thinking very hard about what to do.
I recognize that look. Trying to figure out how the best way to do things, visualize it.
Yep. This person's got their code and they've opened up they had a window open where it looked like they were maybe running some tests.
And there was a
some
question.
More code, running it again.
There was a question earlier online about people were asking what those little red discs are. Those are just earphones.
Yeah, we gave
to the contestants if they wanted to, zone out or focus and keep noise out.
Yep. And there's, of course, bottles of water. Saw a lot of coffee cups there, I think. To stay refreshed for 4 hours.
Now, shortly before the end of the competition, I think 5 minutes till the end, we will have a bit of a countdown and last-minute check of all the scores. So far, it looks like on the scoreboard there's not, in the last few minutes, not too many developments. Am I right there?
Hoss Lyric has jumped to 3rd place.
Oh, wow. Yes.
95 points, not too far off the lead.
Yeah.
But he has left D large, E large, and F large. Any of those would put him in 1st place, but if he's starting work on those now.
But as you had said, he'd been submitting things in parallel in the past, so.
That's true, and he has solved D small, but probably not. He did that much earlier in the contest, probably not using an algorithm that works for D large, or you would think he'd already have done it, but possibly not. It might be that has a solution that he's been kept not submitted yet, maybe running more tests on it in the background on his computer.
Now, in your experience, is this typical of, as you start getting down to the final moments of the contest, there's a lot of jumping back and forth with the scores and the ranking?
Yeah, certainly when time's running out, people who have a solution that they're not certain about, they may just spend the rest of the time testing it. So it depends on their position in the scoreboard. If they think they have a good chance of winning if all their problems are correct, then they can keep testing. But if there's other people, if they have to worry about someone submitting for the same number of points but earlier, then they need to rush it out. But I'd expect a few changes in the last few minutes. Still deep in concentration. got 45 minutes remaining.
So we're going to stay with you as the camera stays in the competition room just to see just how things are progressing in the last 45 minutes of this contest. Gennady is still actually tied for the lead with Eatmore at 101 points. Although with slightly less time for all the submissions.
So he will win the tie break if the scoreboard ends like this.
Yep.
Of course, that's only if their large submissions are correct. And these point totals are how many they'll get if
the larges are correct.
If they've submitted the wrong answer, they won't know until after the competition. So there's still an element of uncertainty there in what position everyone's in.
And Hosler jumped up significantly in the ranks in the last half hour, I believe.
That's right. Yeah, he submitted problem C at around the 3 hours and 5 minute mark and the 6 minute mark for the large.
Last year's champion Mystic is currently ranked at 8th with 73 points.
That's right. He's currently working on problem D. If he solves that, that'll give him 28 more points. That would put him amongst the
top 3.
Yeah, the top 3. Yeah, that would put him in 3rd. Same number of points
yeah.
as Gennady and Eatmore, but with a worse time. So quite a few people in range of 1st place if they manage to solve one of these very hard problems that we've left them. Yeah, you go deep in thought there. He's currently in 5th. He's looking at the hardest problem, problem F. Probably hoping to pick up 22 points there and put him in the lead.
And a question from online from Alexander Giorov asks, can you bring or download sets of code algorithms that are going to be available to you during the contest? And the answer is no.
Not during the contest,
Not during
you
the
can't,
contest.
but beforehand you
Yes.
can set up things that you own or that are public. There's a set
You
of
can
rules
set up your
about
environment, yeah.
what's allowed.
But as soon as it goes, they can't. Once the competition starts, you
Right.
can't download anything.
Right. Yeah, you can't go and search Google for
How to solve.
how to solve these problems. It
Yeah.
probably wouldn't work very well anyway, since hopefully these are all original problems that we thought up that they're working on. Then again, maybe they might sort of have a vague recollection of something that's relevant and want to search for it, but they can't. KCM hard at work there. He's currently looking at paradox sort. We'll get 8 more points for solving that. Should put him up in 8th place. 39 minutes to go. Everyone's still hard at work. No one's in a position where there's nothing left to do. No one has finished everything. Which is good. We try to make these finals problems hard enough that only at most maybe 1 or 2 people manage to finish everything. There's a good distribution of scores. People have solved slightly different sets of problems. They haven't all just gone problem A first, problem B second, problem C third. They've picked and choose based on which problems they like, what they think is the most worthwhile to solve. A lot of people with heads down, pen and paper, trying to think about what to solve next. Most people are on
That
the
looks like the
hardest
face
problems.
of confusion a little bit to me, if I can interpret. Might be wrong, but
Yeah, maybe has a bug in his program, frantically trying to figure out where he's gone wrong. Yeah, certainly.
Now, let me ask, possibly an obvious question. You've been in competitions before. They're in there. They're concentrating very hard. There's cameras floating around. Is that distracting as a coder?
Possibly a little bit. Hey, there's a picture of some of those graphs we said you'd need to be able to figure out that you might be making progress. It's probably not too bad. So the main camera we're seeing at the moment is actually on a floor above. I don't know if we've shown a shot of like a wide shot of the whole room, but no, that's okay. There's some stairs up to a sort of platform above them, so it's not really very distracting. I walked in there and had a look earlier. And yeah, obviously this camera's sort of zoomed in a bit. He's not actually
2 inches from the
2
competitor's
feet
face.
from his face, but and I think people are used to zoning that out a little. Oh, there you go. So yeah, you can see the
we're there.
stairs
Gotcha.
there, and yeah, there's a wide shot, so they're actually not all that much in the faces. No one has a camera right in front of them.
And the whiteboards are there to just kind of isolate each individual
Yeah, we have
station.
people aren't going to be distracted by what's on someone else's monitor, like right in front of them. That's why we have those separators. So I think pretty much everyone looks like they're deep in concentration on their own pen and paper, their own monitor. And of course, very quiet in there. There's not a lot of distractions. If there was, obviously they'd all probably have headphones. Some competitions there is a sort of more of a noisy environment, sort of there are a lot of spectators and a lot of discussion sort of off in another part of the room, but yeah, we haven't done that, so it's all pretty quiet. But yeah, I think regardless of the environment, all of these people are pretty practiced at focusing in on the problem they're solving. No more submissions at the top recently. Oh, there you can see, yeah, that diagram looks exactly like the one I drew when I was solving this problem. I think that's if he's doing paradox sort. Probably trying to think about whether he's really got the right approach or not, and how to turn it into an overall algorithm. There are a few steps. You sort of have to iterate through the possible permutations in a manner such that the first feasible solution you find is the lexicographically smallest one. That's one of the constraints of the problem. So that's sort of the outer part of their solution, and then the inner part has to check whether what they have so far is feasible, which is where all those big diagrams of graphs come in. See people working in multiple windows open. Looks like he's working on his source code and running it, having a look at the output, thinking about it a bit more, swapping between them. Hoss Lyric's still looking at paradox sort, problem D, trying to solve the large. So he's done the small input for the two hardest problems, problem E and problem F. And even those small inputs are worth a lot of points because they are very difficult problems. So if he manages to finish D large, and 9 people have made attempts, so certainly other people competing have found it feasible, he'll actually jump into first. So certainly a lot of possibilities for who might win. It'll all come down to the last 32 minutes. MK Alien and Julgakov both are on 89 points, 12 points away from the lead, which is the value of problem B large. So if they were to solve those problems, they'd be equal in points to the top 2 people, but they'd be behind on time. So they might not necessarily want to be trying to solve those. In fact, Julgakov is, but MK Alien has moved on to problem F. If he managed to solve even the small input for that, that would put him in first.
Now, do you think he has time within the next 25 minutes?
It's a good question. I think it's possible. We don't know how long he's been thinking about it. So, of course, people will often read all the problems fairly early on in the contest and just be thinking about it.
Let it mull over.
Yeah. So if he has an idea of how to solve the small input, he certainly has enough time to implement it. So that's certainly a possibility. And as I said, Julgakov working on B large, and that's a perfectly reasonable strategy. I mean, those 101 points of the first 2 people are not certain because they're based on the maximum they'll get if all their large input submissions are correct. So 101 points with a slower time might still be a winning total. Is he typing with 2 fingers? No.
That's my style.
Looked like it for a minute. Not sure what editor he's using there. It's a very small window.
Yeah.
Could make that bigger.
Oh.
Well, I guess if you can...
Can you tell what problem he's working on? Just too late.
It's a bit too small, the font there, that's okay. But yeah, of course, if he manages to, you don't need to be able to have your whole program on the screen at once. They know what they've written. Another shot of coffee for the last half an hour. That looks like, yeah, I think he's working on paradox sort.
Paradox sort.
And Vepafanov has jumped to 3rd place with 101 points. Like the other 2 people on 101 points, he's solved all of A through D and E small. But with a total penalty of 3 hours and 33 minutes, the time that he reached that score. It's actually the time they've taken to reach that score plus a 4-minute penalty for every attempt at the small input that was wrong if they did eventually solve that small input correctly. So slight technicality there, but mostly it's about who got to that score the fastest. We actually have, each problem is opened by someone. There are people working on every problem in the set. Don't know why one person has problem A open even though they've already solved it. That's a bit strange. Maybe they had it open in an old tab. But certainly most people are on one of the last 3 problems, the ones worth the most points.
Well, as it stands now, it looks like Russia's making a very strong showing.
2nd, 3rd, 5th, and 6th place at the moment. Those are provisional points, of
places,
course.
yes,
yeah.
but
He seems pleased with himself. Possibly just figured out a bug and corrected it. Just staring at his monitor there. An even split between people who are rapidly typing out their
and
last bit of code and
intensely
people
thinking.
who are thinking about what to do.
It has been a long day for all of them.
Well, I don't expect them to have slacked off. I think when you get to this level, you're probably able to spend pretty long stretches.
So this
working out
contestant is
difficult
not
problems.
sleeping, he is thinking.
Down thinking. He's got a multicolored diagram going on there.
I think it's a Google pad.
Yeah. Oh, yes, so it is. You can just see the GLE at the end.
Yeah, I can't make out what he's...
something.
It looks like some sort of tree on there, though.
Yeah, we give them big pads of paper. I guess he drew over the front page with a logo. Got a hoodie there. Almost looks like a poker player. Trying to avoid giving away any tells.
They should do that.
I'm not sure
They should all wear the glasses and the hat and the hoodie.
I'm not sure it's so important to avoid tells in a programming competition, especially since there's a scoreboard right there.
Now, what are the odds that someone is sitting on a large solution to F and waiting to submit?
Well, it's quite possible if you, with a limited amount of time left, they're not going to be able to finish anything else really within the remaining time, unless they had a nearly finished solution to something else. And it would be a safe bet that a submission to F large would win it for them. So they may just spend the rest of the time running tests. But Gennady has just submitted E large.
Oh.
For 35 more points. So that puts him quite clearly in the lead. As long as his solution's correct. So it'd be quite difficult to catch him now. He's the first to reach that score. There's 4 people at his old score at 101. So if they submit E large now, they'll catch up to 136 points, but with a worse time. So
And with approximately 24 minutes left.
Yeah, that won't help them. But of course, they can possibly win if Gennady's made a mistake on one of his 5 large input submissions. So it's not all over yet. And of course, a submission to problem F, small and large, would be worth even more points than that. So it's still within reach of a lot of people. There are 5 people who are working on problem F. Soon to be joined by Gennady when he moves on. Or he might just give up. There's not a lot of time left to start from scratch, but he would have to solve F small faster than he solved the easiest problem, A small, which took him 31 minutes. which would be quite impressive, but you never know, maybe he's partway there already. Since he was looking at that problem earlier on. Everyone's still working right down to the final minute. And of course, we're still answering any questions you might have with the hashtag CodeJamFinals question. On either Twitter or Google+. Eatmore has made an attempt at problem E. We said that, didn't we? So he's been hard at work on problem F for a while. So there's a chance he might catch Gennady.
Who are the people moving around in the room? I guess they're not contestants.
Some of the organisers there.
Yeah. It's just the first time I've seen that.
Yeah, there's just some people working the cameras and...
He looks like he's checking something graphically.
We're at the 20 minutes to go mark. There's Ivan Popolishev, currently working on problem F. If he manages to solve that, that should put him in the lead. But time's running out.
We're under the 20-minute mark now, I believe, right?
Hmm. His head down there for a minute. Looked like he might have been taking a nap or giving up, but then suddenly sprang back to his keyboard. No one's giving up yet.
There's always an energy rush in the last 20 minutes of anything. That was an interesting interaction. Looked like he had something figured out, but it wasn't the result he wanted.
Time running out to implement any new ideas. Eatmore's submitted F small, putting him on 123 points. Just solidifies second place. But if that algorithm generalizes to a solution to F large, if the same program will solve both, then we might see a submission to that following up quite quickly. With only 16 minutes to go, and that's the only thing he has left to solve, he'll probably be doing a fair bit of testing to try and make sure before making a submission.
Now, although the competition ends in the next 15 minutes or so, there will be an hour break, but the live stream will continue, and we'll be back at that time to have an overview of the problems and the announcement of the winner.
That's
just
right.
a reminder.
So, yeah, Bart and Igor, who we had in earlier, are going to go through on a whiteboard, describe the solution to each of the 6 problems. Partly for you at home, partly for the sake of the contestants who
I've
might
just
not
spent
have
the
finished.
last 4 hours working on them very hard.
Might be wondering how it is that you solve especially F large that no one's got yet. And then we'll be going through the scoreboard, and we'll find out whose submissions are correct and whose aren't. I'm looking at Eatmore's solution to F small now. It's certainly not any sort of brute force solution that can only work for F small. He might have a chance of generalizing this to work for F large. We'll just have to see what he manages to do in the last 13 minutes. Let's take another look at the scoreboard. You can certainly open that at home. It's a public website. There should be a link there. Gennady there on 136 points, currently in first, but remembering that these are the points they'll get if their large submissions are correct. And you can see Eatmore in second place has solved the same number of as problems as Gennady, but they're worth slightly fewer points. Gennady had an E large solved, whereas Eatmore has F small solved. Eatmore made an attempt at E large, but his time expired for that. So, as we said before, you have 8 minutes to solve a large input. When you say you've got a solution, you click on the website and say, I want to submit this large input. Then we send you the input file. You have to run your program. It's got 8 minutes to finish, and then you upload your solution. So if the program was slower than Eatmore was hoping, then that can be what happens. You run out of time. Or if the program had a bug and it hung or it crashed, then you won't be able to submit your answer within 8 minutes. But he's currently hard at work on problem F large now, so certainly still in with a chance. Only 11 minutes and 30 seconds left. You also saw on the scoreboard, if you have it open, a lot of wrong tries on small inputs.
Ivan Popolishev just got a wrong try for a small input for problem F.
Yes. So if he manages to fix that solution in the remaining time, he can jump up to 9th place, I believe.
Gennady's still holding on to first.
There's still 64 points in total up for grabs for problem F. So all those people who haven't solved it yet, if they're hard at work on it, they may race ahead right in the last few minutes. Any of the top 14, I think, at the moment are within range of that. We have 6 people have that problem open, problem F. 11 people have problem E left. Certainly the fact that Gennady made an attempt and solved it, as far as we know, maybe it's not correct, might have given everyone else a hint that it's feasible, so they've decided to go to that problem rather than problem F. So that's a problem, like we said, where even the small input's quite difficult. The sort of standard techniques don't quite work. You need to get a fair bit of insight into the mathematics of it, and even more to get the large input. They could be working on heuristic solutions that try a few different methods of attempting to get an answer that they're not entirely sure are correct. If they haven't thought of an algorithm that's guaranteed to be correct, they might be tuning those in the last few minutes. They'll make a submission when they're almost out of time. About 9 minutes to go, so we're in the range where the 8-minute limit to submit a large after you download it is basically the rest of the contest. So you might see people just taking whatever they have and throwing it at the input now. See if they get the answer.
So in the next 20 seconds, they'll have to submit that large input, right, John?
Well, they can start solving it at any time up until the last second. But yeah, so they download the input when they say they're ready, and then a timer starts for either 8 minutes or for just whatever the rest of the contest is, if that's less than 8 minutes. So they can still try and make an attempt when there's only 3 minutes to go. Say, it's just their program will have to be so fast that it can solve it within that time.
Has that ever happened?
Yeah, it's certainly feasible. The problem sizes are set so that an algorithm that we think is efficient enough, we sort of have an algorithmic efficiency in mind, will fairly easily run within the time limit. And that's partly because we allow them to use whatever language we like, and some languages, the programs tend to run a bit slower than others. So if someone writes the same algorithm in C++ as someone else did in Python, we want those solutions both to pass. So we need a fairly big buffer within those 8 minutes. So most of our solutions that we prepared before the competition can solve these problems in, for example, 1 minute, even though we give them an 8-minute limit. But a solution that's less efficient than that isn't the one intended, might take half an hour or something, so it'll be clearly too slow.
All right, with less than 5 minutes to go, if we look back at the scoreboard again. So we still have Gennady in first place. Again, as we have said numerous times, this is all predicated on the fact that the large inputs they've submitted are indeed correct.
That's right.
That being true, Eatmore in second, Epifanov in third. Actually, third through 7th place are all tied at 101 points. So there's a lot that can happen in the next 5 minutes. Now, normally, John, have you seen the last 5 minutes is where all the things start happening?
Yeah, well, it's the time
Score-wise.
where if anyone has a submission that they've got ready that they haven't submitted yet, then they need to do it now. So there could certainly be a lot of attempts coming through. Whether or not they'll result in an improved score. Eatmore, in fact, has just now submitted problem F large and taken the lead, of course, predicated on that problem, that being correct. So he's got nothing left to do now. The competition is over for him.
For him, he's done.
So that'll certainly be interesting in the presentation in an hour. Everyone will be waiting with bated breath to see whether Eatmore's solutions hold up, especially to problem F since it is so difficult. Certainly a lot of Google employees tried it before this competition, and I think some people took much longer than 4 hours to solve it. Some of them came back to us several days later with a solution. So it's certainly a very impressive
Mystic
effort.
has just jumped up too. He just submitted F large.
Wow, that puts him in
Second place.
second place, just 1 point ahead of Gennady.
So as you remember, Mystic was last year's champion,
That's right.
and he had
Well,
slipped down in the
yeah.
rankings today fairly far, but I guess
Yeah.
he's come back and
There's
submitted
a chance
things.
of a repeat
Yeah.
if Eatmore's got something
That's
wrong.
Mystic on screen right now.
Yep. He's just sitting there waiting. So he hasn't solved D large.
It looks like he's
Or
got something going.
E-large.
He's typing furiously right now.
What's he doing? Maybe he hasn't actually sent it up to the website. He's just started an attempt. But yeah, we certainly don't know whether or not Eatmore and Mystic have solved F large correctly. We just know they've made an attempt.
Well,
So the
Mystic can
smart-
also,
Smart thing to do if they have a solution and they're not sure it works and time is rapidly running out is that they should just have a try.
Mystic can still work on E large and D large or submit them
He could.
if he's got them.
Yeah, don't.
He may have been pouring all his energy into F.
Yeah, or it's possible he had solutions to them written earlier and he's been running tests against them in the background and will now suddenly snap off a solution to those as well.
And we're at 3.5 minutes.
Certainly, yeah, cutting it close to the line if that's what he's doing, so probably not. Gennady, as we said, he's made one wrong try at F small. He's probably working up one last try at that in the time remaining.
Again,
Some
we're looking
code
at
there.
Mystic. Yeah.
Yeah, that's not very much code typed yet. Maybe he is trying to solve all of D large or E large
he
in the
might be.
remaining 3.5 minutes. I'm not sure it's even possible to type that fast, even if he knows the answer. Maybe that's not what he's doing. We can only see one window he has open.
We can speculate. That's half the fun.
Yeah.
And we're about at the 2-minute mark. We're still holding at the current rankings.
Two minutes left to go. Certainly expect Hosleric to at least make an attempt on D, E, or F large. He solved the small of each of those. Presumably he's been working on making one of those more efficient in order to solve the large. Possibly he's trying to do that now.
All right, we're pretty close to the 1-minute countdown until the competition portion of 2014 Google Code Jam ends.
That's right, and as we said, we'll be back about an hour after that with a review of the problems and how to solve them, and then the all-important announcement of the results, and we'll see whether these F-large submissions from Eat More and Mystic are correct.
And I think that would actually be a really interesting part to stay tuned for in the live stream when we come back, is because they're going to walk through each problem and show exactly how it's solved.
Right,
which is, even if you don't understand code, which would be me, it's a really kind of fun thing to see how all the thought and all the math that goes into that.
Yeah, we can see how these relatively simple problem statements can turn into sort of some quite complicated computer science that has to be employed in order to solve them. Imagine when the time runs out in 1 minute, everyone's going to mob Eat More and Mystic and ask them how they solve.
I think we're down.
F-large.
I've been refreshing like mad. I think we're down to about 20 seconds. If the website is
8 seconds to go.
okay. Now it looks like Bart is in the room making an announcement.
3, 2,
Announcing the end of
1.
the competition there, and yep, it's finished.
That's it.
No more submissions. So at the moment, we have Eat
Congratulations to
More in
all of
first,
you on
provisionally,
completing
with
the World
165
Finals
points.
of CodeJam 2014.
Mystic second with 137. Gennady in third with 136. But of
How'd you
course,
like
these
the
aren't the
problems?
final results.
Good.
Only the small input submissions. Do we know do we know whether they have them correct? The large inputs, these are just points that they will get if they're correct. And that will be announced in an hour when we come back on the live stream.
And for the next hour, the finalists will end up chatting, decompressing, and having a small reception before we do come back and have the solutions and then the big reveal.
Right. Yeah, so there they are, getting up, stretching. It's been a solid 4 hours sitting down working. I bet they'll probably all go directly outside. You can see in the corner there, there's a door there out into the sunshine. They can enjoy the rest of the sunny Los Angeles day.
And be sure not to leave. Keep this open on a browser. We will be back in 1 hour at 5:30.
Well, there we've, yep, they're all getting up and chatting to each other. Tension's gone. Anyway, we'll be back in an hour.
That's it. 1 hour for the reveal. Thank you.
You guys are going to have a lot of time to talk about the problems. So right now, it's dead in the room. There's going to be food. There's going to be beverages.
This way. Yes, I'm talking to you, Igor Kulikov. I'm talking to you, Mystic. I'm talking to you, other collection of Russians and Eastern Europeans.
Sorry guys, gonna head out of here. Thank you.
Достижимость эквивалентов.
Delicious food for you guys. So.
This is going to be broadcast over the internet. So we're going to have a quick introduction once it comes back on. And then
Set it away from me, right?
Yeah.
I was going to do it.
This does not work. I don't know when they're turning it back on.
Headset. Needs a headset he can't hear.
Right. Yeah, he's gonna.
Welcome back to the final of the 2014 Google Code Jam. Coming up very soon are the final results. We're going to find out who the winner is. But first, we're going to do problem reviews. We're going to talk about the 6 problems they were solving and how they're solved. So doing that is going to be Bartholomew Faro, and first, Igor Novuniak. Take it away. Hi. So everybody's really hungry, so we're not going to spend a lot of time talking about the details of the problems, but let's just try to give you a quick idea of the main theme of each solution. So let's start with problem A, which is checkerboard matrix. Most contestants solve this problem. Let me remind you what the problem is about. You're given a matrix of zeros and ones. It's a grid of these things. And you have to figure out whether it's possible to swap rows or columns and produce a checkerboard pattern. And you want a minimum number of these swaps. So the first thing to notice is, let's try to work backwards. So all these things are reversible. If you swap 2 rows and you swap them again, you get back to where you were before. So instead of going forward towards a checkerboard matrix, let's try going backward. So if you start with a checkerboard, 0, 1, 0, 1, 1, 0, 1, 0, you notice that there are only 2 kinds of rows. There's the 0, 1, 0, 1 row, and there's the 1, 0, 1, 0 row. So we can call this row of type A, and this row of type B, this row of type A, and the row of type B. And swapping any 2 rows doesn't change the kinds of rows you have. You just move them around. And swapping any 2 rows doesn't change the kinds of columns you have. It may change a kind of column, but it will change every column in the same position. So if you have columns of type, let's call them C, D, C, D. These are types of columns. You may change what C means, but the pattern of these C's and D's will stay the same. So what this tells us is that we can solve the rows part of the problem independently from the columns part of the problem. So to find the minimum number of swaps, find the minimum number of row swaps, followed by the minimum number of column swaps, and we get the answer. So one trick to remember is you don't have to have a 0 in the top left, which is the thing that caught a few contestants. You can have the 1, 0, 1, 0, and then 0, 1, 0, 1. So that's a valid final state as well. So how do we find the minimum? Well, given that there are only 2 kinds of rows, and we're going to start swapping rows first, then after we're done swapping rows, so let's say we start with something like this. This is our initial position, which is not a checkerboard. Then we need to swap some rows. So once we've done swapping the rows, we're going to have to end up with either a 0 or a 1 in the top left corner. And we don't know which one it's going to be, so let's just choose one and go with it. And then we'll choose the other one and go with it. So we have to solve this problem twice. So what we do know, though, is that, first of all, there must only be two kinds of rows. So this is a row of type A, and this is a row of type B. And this is a row of some other type, which is neither of these. So this problem just cannot be solved. But if you do have only two types of rows and exactly the same amount of each type, then you know what to do if you're going to swap them around and end up with a 0 in the top left. And then you repeat the same thing for columns. And then you check whether you end up with the checkerboard. And if you do, then out of your 4 tries, so you have 2 choices for whether it's going to be a 0 after the row swaps, 2 choices whether it's going to be a 0 after the column swaps. And for each of those 4 choices, you find the one that takes the least moves. And that's basically it. All right.
All right, I'm coming to talk about Power Swapper. So, thanks, Igor. Okay, so Power Swapper, you have a permutation of the numbers from 1 to 2 to the n. So let me just give a small example. So you might have the numbers, oh, I don't know, here's a really simple example, 1, 2, 3, 4. That's a really simple permutation of the numbers from 1 to 4. You could have 2, 1, 3, 4, variety of things. Now, you want to restore this permutation to the sorted list 1, 2, 3, 4. But you're only allowed to do certain things when you're restoring this permutation. You're allowed to do a single swap of any single elements. You're then allowed to do a single swap of any 2 elements next to each other, but those 2 elements have to start an even index. So I could swap 2, 1 with 3, 4, and let's suppose this kept going with 5, 6, 7, 8. And I could swap 2, 1 with 5, 6, and I could swap 3, 4 with 7, 8, but I couldn't put 6, 7 anywhere. That's no good. So you can do swaps with size 1, swaps with size 2, swaps with size 4, 8, 16, 32, and so on, all the powers of 2 up to the size of the thing. And the question is, how many swaps, how many different ways could you do these swaps to get back to a sorted matrix? Okay, so a couple of things to observe. One thing is that you only have one swap of size 1. That swap has to fix all groups of size 2. Okay, so right now, this is feasible because I can swap the 1 and the 2. But if I had, for example, if I had 3 different groups, 3 different of these pairs that were all wrong, a single swap couldn't fix them. And later swaps won't help. Swaps with size 2 won't help the groups of size 2 because they just leave them alone and move them around. Swaps of size 4 won't help the groups of size 2. So the swap of size 1 has to fix the groups of size 2. The swap of size 2 has to fix the groups of size 4, and so on. Now, it could happen that you have either 1 or 2, well, okay, or 0, possibilities for fixing the groups of size 2 with swaps of size 1. Okay, so I had something written down here, but I've forgotten it now. Ahmed, what's the sequence? 1, 4, 3, 2. Okay, so there are a couple of ways of fixing this. So 1, 4 isn't good, 3, 2 isn't good. I could swap the 2 and the 4, and that would bring us to 1, 2, 3, 4. So both of our groups of size 2 are good. Or I could swap the 3 and the 1. And then that brings us to, 3, 4, 1, 2. And then again, both of our groups of size 2 are good. At this point, we can brute force. We can say, all right, let's try both of those. Let's do each of those and then see what future swaps we need. We're just going to backtrack, okay? It may seem horribly inefficient, but it turns out that because you only have at most 2 to the 12 items in this list, and you are only going to do 12 swaps, you aren't going to backtrack more than 12 times. It turns out, fun fact, you're not going to backtrack more than 6 times, but the proof is left to the reader. So your running time is going to look something like 2 to the 12 times 2 to the 12 to iterate through this entire list every time you backtrack, which is 2 to the 24, which is about 16 million, which your computer can handle no problem. So that's how you figure out which different sets of swaps can work. Another key thing to note is that order doesn't matter. So if in this example, I could do a swap of size 1 and then a swap of size 2, I also could have just done them in the opposite order. I could have done the swap of size 2 followed by the swap of size 1. It doesn't make a difference. So if what I'll do is I'll do this backtracking, and at the end I'll say, okay, I had one solution with 3 swaps, and one solution with 4 swaps, and one solution with 5 swaps. Then the answer is 3 factorial plus 4 factorial plus 5 factorial, because those we could have done these 3 swaps in any order, these 4 in any order, and these 5 in any order. So that's Power Swapper. Over to Igor for the next problem.
So the next one is called symmetric trees. You're given a tree. The tree has colored nodes, and you want to know whether it's possible to draw this tree in a plane with a line of symmetry. So the first thing we're going to ask is, how many nodes of the tree actually fall on this line? Could be 0, could be 1, could be more than 1. So the 0 case is the easiest one. If no nodes fall in the line, and there's a line of symmetry, and we have at least some vertices, then there must be a vertex on this side, and there must be a vertex on this side, and there must be an edge between them, and it better be horizontal, because otherwise it's not symmetric. And there can't be any other edges crossing the line, because if there were some other edge, then we would have a cycle, because you would have to have a path on this side and a symmetric path on this side. So there must be exactly one edge. And now what happens on this side, there's some tree going on here, and there's some tree over here, and they better be symmetric. That's one case. And the other case is we have a vertex on the line. So if a vertex is on the line of symmetry, then let's look at its neighbors. So it will have either an odd or an even number of neighbors. So first of all, if it's an odd number of neighbors, then one of those neighbors must be on this line, because otherwise you can't have symmetry. If it's an even number of neighbors, or at least for all the other ones, whichever ones go to the left, there must be a symmetric neighbor going to the right. And whatever tree is here has to be symmetric to the tree here. So we'll look at all the neighbors, and we see if we can pair them up. So if the subtree that is identified by going in this direction from our vertex is exactly the same as the subtree going in this direction, then we can pair them up, and we do, because there's no point otherwise putting them on the line. So for both of these things, we're getting to the point where we have to be able to identify some subtrees. So for every edge of the tree, let's say you have an edge, you think of it as 2 different edges, one going in one direction and one going in the other direction. And every directed edge uniquely identifies a subtree, because you can think of the directed edge as pointing to something that happens over here, whatever the rest of the tree is. So a subtree is equivalent to a directed edge. So now, for every directed edge, you can compute what the subtree is. And if you want to speed this up, then you can compute some kind of a hash code. It doesn't really matter what kind, as long as it's reasonable. You compute some representation of the subtree. It could be a hash code, or it could be just some kind of compressed representation that is easy to compare. All you need to be able to do is to say, for 2 directed edges, do they point to exactly the same kind of subtree? So to test whether you're in this case, you try every edge, and you compare the subtree identified by this edge to the subtree identified by this edge. And if they're equivalent, then you found a symmetric representation, and you say yes. If not, then you try to find one of these cases. So you pick a vertex, and you're going to try every vertex. And for this vertex, you look at its neighbors. You look at all of the directed edges coming out of it. And for every subtree, if there's another subtree with the same hash code or the same representation, then you put them on opposite sides. If there aren't, then you could have 1 or 2 or 3 or more of them that are not paired. So first of all, if there are 3 or more, then you're screwed. You can't do anything, because you only have 2 directions to go, which are not left or right. If you have 1, then you just pick a direction and you go in this direction. And now for this vertex, you sort of do the same thing. You find pairs, and you try to pair them up. If there's another one coming out of here, then you have to go in this direction and do the same thing for this vertex. And you kind of keep going. So if you've paired all of the subtrees of this vertex, then you're done. If you haven't, then there's at most 1 that must remain, because you only have 1 direction to go. So you might end up building this chain with these subtrees going like this. So this one matches this one, and then here, like maybe this one matches this one. And if you want to speed this up a bit, then you realize that you never need to start with a vertex that has an even number of unmatched ones, because if you're just testing all the vertices anyway, you should start with the endpoint of a chain. So you only consider ones that have exactly one unpaired subtree. And if you have this comparison implemented, then you can match them quickly. All right. And now we go into paradox sort. So now we're getting into some really hard stuff. So for this problem, I apologize beforehand. I'm going to gloss over a lot of important details, because otherwise it will take too long and we will all die of hunger. So paradox sort, thanks. Let me remind you. We have a sequence of candies. Each candy is an integer. And we're going to take one candy at a time. We have the first one in our hand. And the next one that comes in, we're going to compare. And if it's better, then we throw away the old one and keep the new one. If it's worse, then we throw away the new one and keep the old one. And we keep doing that, and the question is, can we end up with some target candy? And usually in these problems, and then at the end you say, and out of all the possible situations, you want to find the lexicographically smallest ordering. And that's usually a sign that this problem is harder than it sounds. But in this case, it's actually a hint on how to solve it. So if we're looking for the lexicographically smallest ordering, then let's just start building it in order. So we will say, well, what is the lexicographically smallest it could be? Well, it could start with a 0. So let's try a 0. And if we try a 0, and we can still have a way of ordering everything so that we end up with our target t, then we can keep the 0. Otherwise, we can't take the 0, and we have to take a 1 instead. So the only thing we need to be able to do is figure out, given the sequence of candies we've chosen so far, and given that we have candy H in our hand, and there's possibly some other candies after that, and we're going to try to get to target T, can we place a particular candy here? And we're going to place the smallest one possible here and see if it's possible. And if it's not possible, then take the next smallest one and so on. So this is the one we currently have in hand, H. This is the one we want to end up with, T. And we have this bag of candies still sitting there, like A, B, G, K. So we take the lexicographically smallest one and we stick it in here. And we want to say, let's consider candy O, because we've already discovered that A, B doesn't work, G, K doesn't work. Maybe we have X and Y. So O is our next candidate. So what we need to answer is, there are two cases. First of all, if this is an O, if it beats H, then we're going to start holding on to O. If it doesn't beat H, then we're still going to be holding on to H. And in any case, we need to figure out, can we place these candies somewhere? It doesn't really matter where, as long as it's some valid ordering that gives us T in the end. So let's consider the following representation. So let's have an edge between two candies, which means that there's an edge going in this direction if when you're holding this one and you see this one, you're going to switch. And we know that there's either an edge going this way or an edge going this way, never both. That's the definition of the problem. So for each of these candies, we're going to try to build a tree out of T to try to figure out what are all the things that lead to T eventually. So let's find all the candies that have an arrow to T. So maybe we have an A that points to T. Maybe we have a B that points to T. And maybe we have a G that points to A. So essentially, we're doing a breadth first search or depth first search. It doesn't really matter if G points to both A and B. It doesn't matter which one we choose. We just want to know the set of candies that have paths to T. So let's say we found them all. If we don't have any more left, then we're actually done. We just we list them all in reverse order in such a way that all the arrows point to the right. And it doesn't matter what the order is. Whatever candy we pick, it has some arrow pointing right until we end up in T, and everything's good. The problem is, what if we still have some left? So now we consider candy H, which is our current. So H better be on this tree somewhere, because if it isn't, then we're never going to get into this train. So this is the good set. Once we get into this set, we have a path to T. So we check if H has something pointing to this tree. If it doesn't, then there's no solution. So then maybe we can still have some left. So at this point, we actually have one more chance of having a solution. If there's some other candies like X that have a link to H, a direct link to H, then we can actually stick this X right up here. And since H is our current, and X has a pointer to H, that means H doesn't point to X, so we'll just skip over the X. And maybe Y also has pointer to X. and we can stick Y over there and still get it for free. The problem is, if we find something else, like Q, that still remains after this whole operation. It's not in this tree, it's not H, and it doesn't have a direct link to H. The only thing it maybe has is a link to something that has a link to H, then we can't put it anywhere. Because essentially, however you order these things, you're not going to have a path to T. Because the only way to get to T, let's say if there's a path only to X, then you're going to have to go through H, but you can't go through H twice because you've already hit H once. So essentially, it's a few cases that you have to cover. And the hard part is convincing yourself that these are all the cases that you need. And if you don't hit one of these cases, then there is no ordering that could be here that would hit T eventually. You will get stuck in some dead end that doesn't have a path to T. So as promised, really hand wavy, but we will post full editorials later. If you have more questions, or you can ask us at dinner. And we'll talk for hours.
All right, so now that all the easier ones are out of the way, onto allergy testing.
You can take this otherwise.
Oh, thanks. Okay, so allergy testing started out life as the easy problem for round 2. When it was the easy problem for round 2, it had a very small limit for N and a very small limit for A and a very small limit for B. So for those of you who haven't read the problem or don't remember it, in allergy testing we have N different kinds of food, and N could be very large. It could go up to 10 to the 15. And we have 10 to the 15. And we have A, which could be up to 10 to the 12. And B, which can be up to 10 to the 12 as well, and it's greater than A. Okay, so in its original life, N was like 1,000. And the way to solve that problem there is a fairly standard dynamic programming algorithm. As most of the people here probably know, you can figure out the amount of time it takes to figure out N different foods, and that depends on the amount of time it takes to figure out N minus 1 different foods, and it depends on the amount of time it takes to figure out N minus 2 different foods, and so on. And minus 1 depends on minus 2, and minus 3, and so on. And so you've got these links, but you can figure them out as you go along, and this is dynamic programming, and you can solve this problem. And then we had the idea, well, why can't we just raise N up to 10 to the 15? Is this still solvable? And this is back in the ancient days when A and B were still 100. And when A and B are still 100, which is what it was for the small solution here, you can change this function T of N, which is the amount of time it takes to figure out N different foods, to a function N of T. So the number of foods you can figure out after T days. And when N is 10 to the 15, and A and B are only up to 100, then the answer never gets higher than log base 2 of 10 to the 15 times 100, which is 5,000. And if you checked your output files for the small, probably there were some 5,000s in there, because that's the largest possible answer for the small. On the large, though, the largest possible answer is this log base 2 of 10 to the 15 times 10 to the 12. That's less feasible to just check all of them. So how do we go about this? Okay, so we're still going to be relying on this idea that we compute the number of foods you can distinguish between in T days. And what we're going to do here is we're going to think of it like a decision tree. So the tree I'm going to draw, we're going to start off with how many different foods can you figure out if you have 0 days available to you? Well, if you have 0 days available to you, then it's okay if there's only 1 food left, right? If you have 0 days to spend and there's only 1 food left, you know it must be the one that you're allergic to. Okay. So let's say that you have 1 day. Sorry, I forgot to tell you the parameters of this example. In this example, I'm going to use A equals 100 and B equals 200. Okay? So if you had 100 days available to you, how many different foods could you distinguish between? Well, you don't have time to have an allergic reaction and then do anything after that. You only have time basically to eat 1 kind of food and then not have an allergic reaction to it, or have an allergic reaction, but that lets you figure out what the other food was. So this actually lets you deal with 2 foods and down here we have this one here, which is that if you have an allergic reaction, it still takes up 100 days, but you figure it out. And so the tree's going to grow up like this. Whoops. Well, I gave away the answer there, but if you have 200 time, then you can deal with 3. But then something magical happens once you hit 300 days. Once you hit 300 days, then you suddenly have some time to spend on having an allergic reaction, and then figuring out something after that. So if you have an allergic reaction, then you can take, and this is a longer edge deliberately, though maybe not this much longer. Then you can take this time, have your allergic reaction. That takes 200 time. You have 100 time left, and with 100 time left, you can distinguish between 2 things. So what this is telling us is that if you have 300 time, you can eat 2 foods and have 3 left over and still figure out the answer. So that's fine. So the main reason I'm giving this
Is that just not working?
Okay, so the main reason, hey, I'm much more audible now. So the main reason I'm giving this example, which I'm sure you all heard, is to make sure that we understand this format, because I'm going to get a little bit more complicated with it. So what we have here is we have, I'm just going to look at my notes because I had something really clever to say here. We have a tree in which we want to fit the maximum number of nodes in this binary tree of depth t, where left edges cost a, left edges have depth a, right edges have depth b, unless it's the last right edge, and then it has depth a. Okay, so we're trying to cram nodes into a binary tree of depth t, or of some constant depth. So, all right, let me move on to the hard example here, because the hard example comes when instead of 100 and 200, I guess let's move to the other board here, instead of 100 and 200, let's say that n is still 10 to the 15. Let's say that A is 1 and B is, let's say, 10 to the 9. Let's say, okay, so 10 to the 9 is the really hard example, right? Because the answer grows very, very slowly, like the number, or very quickly rather. The number of, you basically only eat 1 food at a time for the first billion days, which is a little bit tedious, I grant you. So I'm going to actually draw out an example like this for B equals 1,000 very quickly. And it's going to look sort of similar to this example. And I'm not going to actually draw in everything. So you're going to have a tree that looks like this, like this, like this, like this, and it's going to keep going like this. And so your nodes are going to be numbered 0, 1, 2, 3, 4, and your answers are going to be 1, 2, 3, 4, 5. So you'll notice that the answer is simply linear. So this is n of t, the number of foods you can figure out given time t. The answer is linear. Something special happens though when you hit 1,000. I probably should have left myself a little vertical room here. So then a miracle occurs. Okay, so now we're going to hit 1,000 days. And at 1,000 days, you still don't quite have time to spend on allergic reactions. So the answer here is going to be 1,001 still. It grew linearly. And we still have this 1 off to the side. But when you hit 1,002, or B plus A, excuse me, 1,001, which is B plus A, all of a sudden, again, you have time to spend on an allergic reaction. So you have this really long node edge hanging off here because it's way, way more expensive than the 1 node. And you've got 2 time left here with which you can get, or excuse me, we've got 1 time left here with which you can solve 2 foods. Okay, so the answer here is going to be 1,003. The answer for 1,002 is going to be 1,006, because there's going to be enough time to sort out 3 foods afterwards. The answer for 1,003 is going to be 1,010, because you'll have time to sort out 4 foods afterwards. So in this regime, n of t was linear. In this regime, n of t goes up first by 2, then by 3, then by 4, then by 5, then by 6, then by 7. In this regime, between b and 2b, n of t is quadratic. We can easily write down closed forms for these just by looking at the numbers and saying, and figuring out what they are. It's a little trickier if A isn't 1, but I trust you all to be able to do this. You can write down a closed form for for small n, for small t, t less than 1,000. So let me go back over to this board and stop talking over myself here. So for t less than or equal to b, we have linear. For t less than or equal to 2b, we have quadratic. And more than that, we get cubic at 3b, or at 2b, and then at 3b we get quartic, and so on. But I'm not going to write down closed forms for anything after quadratic because that's boring. I'm just going to do closed forms after quadratic, and probably someone could actually go through and figure out what the cubic is, the quartic is, the quintic is, and actually just solve the problem that way. But once we get past the quadratic, then t of n is n of t is growing. So n of t, those of you who did a bunch of computer science are going to love this, which I'm guessing is a lot of you, grows like t cubed over a. So n of t grows really fast. And since n can't be more than 10 to the 15, its cube root can't be more than 100,000. So now we're back in the regime where n of t is actually, you don't have to check very many t's to figure out n. So now we can go back to this dynamic programming algorithm that we were using earlier. If we need to look up what n of t is for a given t, we either, if it's less than or equal to b, we just look at the linear equation. If it's less than or equal to 2b, we look at the quadratic equation, and otherwise we figure it out in our lookup table. There's one last step for this problem, which is that because this grows like t cubed over a, if a is really big, like if a is 10 to the 6th, then it's no longer 10 to the 5th steps, it's 10 to the 11th steps. We have to be careful to only look at numbers of days that are interesting. And an interesting day is of the form p times a plus q times b. There are a lot of things like that, but the key thing here is that q can never get more than 50. Very exciting fact. So q will never get more than 50 because 2 to the 50 is about 10 to the 15. You're always going to eat fewer than half of the things. So if you have an allergic reaction, that's eliminating more than half of the stuff. So you're never going to have more than 50 allergic reactions, and you you only have a relatively small number of times that are interesting, and you can figure out n of t that way. Okay, that was the harder one to explain. So the final problem of the set is ARAM, which I think is a super cool problem. So like allergy testing, this one began a little simpler. Thank you. Like allergy testing, this one started a little bit simpler. It started off just essentially like the small data where RNG were pretty small. So the idea is that you're playing a video game, and before you start each game, you're assigned a random champion. And you have some probability of winning with that champion, and if you don't like that one, then you can spend some virtual money to get a different one at random, or maybe the same one if you're unlucky. And you gradually accumulate that virtual money over the course of multiple games. So the question is, given a role, or given a particular champion, should I take that random chance and try to get a better one? And that's going to depend on how much of this virtual currency I have left. So you need to sort of come up with a strategy for maximizing your total number of wins. You're going to play a Google Games, and once you've played your Google Games, we want to know what fraction of them you'll have won. Okay, so you have some state. Your state is your number of rerolls. So that's your state. You have a strategy for some state. And your strategy will look like, you'll look at your list of champions, and it'll look something like this. With one guy, you have a 0.9 chance. With another character, you have 0.8. With another, you have 0.53. And so on, and you'll draw a line somewhere, and you'll say, if I get someone worse than this, then I'll reroll. If I get someone better than this, I'll just keep it. It doesn't make sense to say, well, I would keep a 0.1, but I don't like this 0.2. That would be silly. So a strategy is just a line that you draw somewhere. Now, for the small, it turns out that if you pick a strategy for each state, where again each state is how many rerolls you have, the space of strategies is incredibly convex. So if what you're trying to figure out is how many points you'll get for a certain strategy, you can do like a local search. You can do gradient descent. You can do a whole lot of different things, and they will get you to the right answer. So, so just pick a strategy and iteratively improve it, and that will work for the small. And you just have to figure out how many of the games you'll win. It's a Markov chain. You can figure out its eigenvector. I'm not going to explain that now. You can look it up. And that lets you solve the small. The large, though, is much, much cooler. So I'm going to write down an example here. And this example, I'm going to have n equals, I don't know, something big, like 1,000, because that's as big as it gets. R equals 2, G equals 2. So your states are that you have 0 rerolls left, that you have 1/2, that you have 1, that you have 1.5, and that you have 2. Okay. So I'm going to compute something. First of all, what I'm going to do is I'm going to binary search for the answer. I'm going to pick a number, which I guess at first is going to be 0.5. And I'm going to say, is it possible for me to win on average 0.5 games per game? So can I win half of my games? Great question, Bartholomew. Thank you. So I'm going to binary search on this number. So how do I figure out whether I'm going to win half of my games? I'm going to compute something that I call, I guess, a score, which is the number of games that I expect to win relative to this 0.5. So let's suppose that I have 0 rerolls left. If I have 0 and let's suppose that the average of all of these numbers, because I can't reroll, I just get someone on at random, so I get the average probability of winning. Let's say that the average is 0.4. I'm not going to write that down, because what I'm going to write down is the score, which is minus 0.1. So the score for 0 is going to be minus 0.1, because I expect to win 0.4 games, and I'm trying to win 0.5. Okay? So that's actually the score. I'm going to draw a little arrow there. And what this means is that this is the number of games relative to the target that I expect to have won by the time I reach the next state. Okay? After I play 0 games, I know I'm going to reach 1/2. I have no choice. I can't re-roll. And I know that I'm going to win on average negative 0.1 games relative to the target. Again, here, I don't have any re-rolls. Not much going on still, so I'm still going to lose 0.1 games. And now is where it gets interesting, because now I have the choice to re-roll. Now I have to pick a threshold. So let's suppose that I picked a threshold. I'm actually just going to try all the thresholds. So once I've picked a threshold, then I can compute this score to go from 1 to 1.5. Remember, the score is the number of games relative to the target that I expect to have won the next time I go from 1 to 1.5. Now, I might go directly from 1 to 1.5 if I don't re-roll. But I might get like the worst champion, who's named Timo, and I might drop down to 0. And then I'm going to get this minus 0.1 before I get back up there, and then another minus 0.1, and then we're back where we started, and then I'm hoping again that I don't re-roll, and that I get some points. So what the score is going to look like is, so let's suppose that I picked a strategy, and this for 1, and the strategy gives me a probability P of re-rolling. And the average number of wins on the champions that I'll keep, on champions that I wouldn't re-roll, is W. Okay, so then my score at position 1 is going to equal 1 minus P, which is the probability that I don't re-roll, times W, plus P, which is the probability I re-roll, times the score of 0 plus the score of 1/2 plus, and then I'm back there again, and then it's going to be plus score of 1. You'll notice a score of 1 is on both sides of this equation, but that's okay. We can do some dividing and subtracting to figure out what it is. So now this lets me get a number to say, when I'm at a score of 1, I might not get up to 1.5 right away, but I eventually will probably. What is the expected number of wins relative to 0.5 that I will get for that? So that'll be some number like minus 0.02 or something like that. And I do that again to get up to 2. And maybe that's minus 0.01. Okay, so where is this going? What can we do with this? If we could compute the average, so again, the score is the number of games relative to the target that you expect to have won by the next time you reach a stage. If you could figure out that number for some state going to itself, which will happen a lot of times, you're going to play 10 to the 100 games, whatever state you look at, you are going to start, if you start at that state, you will eventually end up back at that state. And that's going to happen a lot of times. If you could get the score from going to from a state to itself, then you would actually know on average how much you gain once in a while. And if that number is negative, then it means you're never going to hit this target. But if the number is positive, that means that you are on average above that target as you play your games. So what we do is we figure out the score for 2. And because your rerolls can't go any higher for 2, the score for 2 is the expected number of wins going from 2 to 2 relative to the target. So if that's positive, then it is possible to get this 0.5 score. And if it's negative, it's not. Don't worry, this is all on tape, and we're going to publish an editorial. So I apologize for any lack of clarity here. I wanted to get through it relatively quickly. So I'm going to claim that it was deliberate. If I said anything mysterious, then it's an exercise left to the reader for you to figure out later. And that's it. Does anyone have any questions about, any brief questions? Maybe time for one, and then we'll get to revealing the winners, and then we'll get to eat. Yeah, I thought that wouldn't give any questions. All right. Ready for winners? Let's do it. Let's get these boards out of the way. Okay. All right, so for those of you who haven't been to the finals in the last couple of years, we have this awesome point revealer system. So what this means, you want to scroll a little left, Igor. What this means, you want to scroll a little right, Igor? Okay, so what this means, I guess you're going to have to drag the window to the right. That's the tab. I believe in you. Yeah, that was my mistake. Okay, there we go. So what you see in the leftmost column is your name and your flag. What you see in the next column is, based on the information revealed so far, which is right now is no information other than what was on the scoreboard at the end of the contest, what your rank could possibly be. The next one is your confirmed points. Next column is your confirmed penalty time. And then after that is each problem. So we're going to start revealing for the large inputs whether you got them right or wrong. You'll notice there are some X's in there for things people tried but didn't eventually get. And I think for some TLEs on larges, they might be X's as well. No, maybe not. Okay, so let's do it. Let's reveal the first score. All right, so Isaiah got B large correct. And some more points for Fao. Exod 40 gets A large. Flasek gets A large. Kawatea gets A large. Kanihora gets A large. A large is going really well. Isaiah now doesn't get D large. So we've got our 26th and 25th locked in. There's another A large. Another A large. There's a B large. You'll notice that a lot of you are still eligible for first place. Exod 40. There's a C large for FH Lasek. Galatea gets a large. Candy Horror moves out to 5th place. Marcin SMU moves up to 4th place. Zhen Kai moves up to 6th. Dmitry Egorov moves up into 1st place. But he is out of opportunities to get more points, so he's going to have to hope that a lot of people get some stuff wrong, but there's still a chance. KCM 1700 gets some more points. Iwi gets a large, still in the running for the victory. Shik gets a large. Dmitry Zholgakov gets a large. Flight 89 gets a large. A large is going really well for you guys. Igor Kulikov, a large. More a larges. Romka, a large. Stya, a large. Gennady, a large. Lufanov, a large. A large, and you'll never guess, a large. Okay, we're doing pretty well here. Yeah, C is a tough one. FAO gets it. Up into 5th place. Exod 40. Very nice. No more chances to get points, but he's in 2nd place. Kotea takes his place in 2nd. Also has got all his points. KCM 1700 moves up to 1st place and still has D large available. Iwi moving up. Shik also moving up there. Dmitry Zholgakov moving up. Flight 89. You guys get a lot of check marks. Igor Kulikov, moving up into 1st place. Okay, L13N gets more points. Alien, hey, that makes sense. Thanks, Igor. Romka, moving up there. Stya gets some points. Gennady gets B large right. Bepifanov, A large right. Ivan Popolishov, B large. B large for Stephen K plus. All right. And D from Marcin SMU. Oh, that's a lot of points there. All right, so 21 through 26 are now locked in. We're now fighting for the top 20. Stya, C large is wrong. Iwi, C large is right. Moving right up the scoreboard. Djolgakov's misses C large. But he still has a chance to get D large, and he nails it. Shik with C large. Makes it into 3rd place, but is out of ways of getting points. Flight 89 moves on up. Romka misses C large and gets D. He's in 2nd place. Gennady, C large, gets it. Bepifanov misses C large. D large takes him into 1st place, but he's out of opportunities to get points. Ivan Populishev, C large is wrong. Stephen K plus, C large is right. Mystic, that is a lot of larges waiting to be judged. All right, A large is right. Eat more, a lot of larges waiting to be judged. A large is right. And he still has 4 more. Wow. Huss Lyric. A large is right. We're in the top 15 now. KCM 1700, C large. He gets it. He moves into 1st place, but he's out of ways of getting points. Igor Kulikov, C large. He's D large. He's got it. Moves into 1st, but he's done too. MK Alien moves into 1st, and he's out of points. Mystic, with his 3 larges left, nails the 1st one. Eat more, 4 larges left, gets the 1st one there. Haas Lyric, 2 larges left, gets the 1st. Iwi, his last large, misses it. 7K plus, moves up into 1st place with his last. And he's guaranteed top 4. Very nice. Gennady with D large moves into 1st place. He's guaranteed top 3. So Gennady is going to be medaling. Mystic with a 2nd last large moves into 3rd. Guaranteed for top 5. Eat more. Guaranteed top 5 with his next large. Haas Lyric, last opportunity to get into 3rd. Misses the problem. We're down to the top 4 here. This is very, very close. We have 4 larges left to go, and 3 of them are on the hardest 2 problems. Let's see what Mystic has to say. And he misses F large. So we have our medalists. Our medalists are going to be Gennady Karakovich, 7K plus, and Eatmore, but in what order? Eatmore's got problem D, and he gets it. And he still has F large to go. So 7K plus is in 3rd place. Congratulations. And Gennady can move into 1st place if he gets E large. He's got it. But now, oh, and Eatmore misses F large. Our new champion, 2014 CodeJam champion, Gennady Karakovich. Come on up. We have a gold medal for you. Congratulations. Now, for those of you who don't know, Gennady would have made the finals 3 times already, but he was under 18 when it happened. So for those of you who would not have made the finals 3 times when you were under 18, that's what happens when you do. Congratulations, Gennady. Could we please have Eatmore come up for 2nd place, silver medal? Eatmore? Congratulations, really well done. And 7K plus for 3rd place, the bronze medal. Come on up. Congratulations. All right. Let's get some photographs. Congratulations, you 3. You guys did really, really well. This is a tough problem set. And I think, oh, yes, oh, could you guys please hold the trophy? Gennady, could you grab the, I don't know how heavy it is. It's kind of, well, okay, you guys can help. Oh, that's probably not good. Why don't you stand behind the trophy, all 3 of you, please? All right, can you stand on either side of Gennady, please? Your 2014 CodeJam medalist. We have medals for everyone else available up here. Sorry, I cut off my own applause line. We have medals for everyone else available up here. I think we're probably done with the YouTube broadcast. So from everyone here in sunny Santa Monica or LA or Venice Beach, thanks for tuning in. And thanks to all of our finalists for putting in an amazing performance.